Yeah, please kindly confirm audio, video, and screen once. Please kindly confirm audio, video, and screen. Okay, fine. Yeah, so let's continue with the yesterday class. So now we are going to check the voltage distribution across a string insulator, right? So before moving to that, first we should know how we will represent a disk in the electrical equivalent circuit. So generally, disk is an insulator, right? Disk is an insulator. It will be represented as a RC circuit, as usual, we said earlier. So we can say it's a RC parallel circuit. Okay, yeah. So let's say here, disk representation in the electrical equivalent circuit. Disk representation in the electrical equivalent circuit. Yeah. See, basically, disk in the sense, physically in this manner. So this is a disk we have, metal cap and metal pin. And then this we are representing as a RC parallel circuit. Generally speaking, if it's an insulator, we have to keep it as RC parallel circuit like this. Simply in this manner, right? RC parallel circuit. But particularly for AC operation, the current flowing through this resistor IR is negligibly small compared to current flowing through the capacitor. For case of AC, in the case of AC, current flowing through resistor is negligibly small compared to the current flowing through capacitor. So this we are going to represent simply as a capacitor for AC operation, right? So this is for AC operation. AC operation. So why it is represented as simply capacitor for AC operation? I already said that IR current is very, very low compared to the current of IC. Next, if you think about DC operation now, for DC, what about this capacitor reactance? It will be infinite. Xc equal to infinite. So it is acting as open circuit. So it will be represented simply as a resistor. Okay. So I'll write for DC operation, current IC equal to 0, or you can write capacitive reactance is equal to infinite. If that's the case, it will be represented simply as a resistor. For DC operation, it will be represented as simply resistor. Okay, now with the help of this, we'll take up a string, maybe suspension string I will take. Then for AC operation, I will draw the equivalent circuit of that, and we'll check how is that potential distribution occurs. Similarly, for DC operation also we'll do. Okay, yeah. So let's take potential distribution across, or voltage distribution across, potential distribution across HVAC suspension type string. Okay, potential distribution across HVAC suspension type string. Yeah, see, I'm showing that suspension type string here. Let's say 4 units here, 4 discs. Okay, so I'm showing here. So it's disc number 1. Okay, yeah. So like that, we have 4 units. Let me show. So it was second disc, I can say, disc number 2, and then disc number 3, and then 4. 4 units we have, right, like this. And on this side, we have a cross arm, I said already, right? And this tower is getting grounded, and this was a conductor. Right? Conductor. Fine. Next. I know already for AC operation, each and every disk we are going to represent as a capacitor. So I will show that. Each disk we are going to represent as a capacitor like this. 4. capacitors like this. We have each disk is having equal capacitance. I can say each disk is identical. Each disk is identical. Each disk is identical. Next thing, next. Kindly understand. Tower is connected to ground. Now you see, I will show some points in this original string what we have brought, this one. I will show some points. Is there any capacitance formation between those points or not? That you tell me please. Okay, listen. This is one point I have taken. This is other point on tower. Can we have any capacitance between these two? Can we have any capacitance between these two? Yes or no? Yes or no? No, because both are operating at same potential, so you don't get any capacitance. Simple. Okay, next. Between this point and tower. Between this point and tower, do you have any capacitance existing? Yes, definitely there will be some capacitance existing because this potential will be definitely non-zero and this is at 0. Because of that, some capacitance will be existing between them. So I will say this capacitance as something like C dash. Something like C dash. Now you please tell me, between this second point and tower, do you have any capacitance existing? Between the second point and tower, do you have any capacitance? Yes. My question is, how will be this value compared to the above number? Is it equal or less or more? Tell me please. How is this number compared to the above number? Is it equal or less? Equal. It won't be less or more. It will be equal. What's the reason? See, generally the value of capacitance depends upon dimensions of the system rather than how much voltage you are going to apply. It will be depending upon only dimensions of the system rather than how much voltage you are going to apply. So that as dimension is same, means if you assume that the string is exactly parallel to tower, is my voice is clear? Any disturbance in the voice you are observing? Please kindly tell me. Please kindly tell me. Is my voice is clear? Small disturbance is there. Okay, fine, good. Let me get. See, if the string is exactly in parallel with the tower, obviously, from each metal point to tower, the capacitance formation will be equal. So here also you get a capacitance of C dash, right? And here also you will get a capacitance of C dash, obviously, right? I will show these capacitances in our electrical equivalent diagram. So I'm showing those capacitances. So these are the metal links, or you can call them as link pins, right? Metal links, or you can say link pins, 1, 2, 3, 4 link pins. And this is that capacitance formation we have, C dash capacitance I'm showing, right? Like this we have. Next thing. Let us say voltages across the units. Generally, I will be counting the disk numbers from top. Disk numbers I will be counting from top. 1, 2, 3, 4. Like, okay. So it's 1, 2, 3, 4 disks. So voltages I am showing now. It is V1 voltage. It is V2 here. And this is V3. And then it is V4 voltage. Like this we have voltages 1, 2, 3, 4. Currents in the capacitors I am showing. Currents in the capacitors. I1, I2, I3, I4. Right? And see what we have here. C that we can call as self-capacitance of each disk. C is going to be called as self-capacitance. Self-capacitance of each disk. Self-capacitance of each disk, or you can say each unit. Okay. And whatever the C dash we have here, C dash, that is going to be called as mutual capacitance. Mutual capacitance between any metal link to tower or link pin to ground also you can say. Okay. Mutual capacitance between link pin and ground. Link pin and ground, I'll say not mutual, it's not mutual. Sorry, I'm really sorry, it's not mutual. You call it a shunt. Mutual will give a different meaning here. You call this one a shunt. Kindly modify that. Don't call it as mutual. Please call it as shunt. Shunt capacitance existing between link pin and the ground or link pin and the tower or metal link and the tower. All the terms will be same. Fine. Next. See, these capacitances, C dash, C dash, C dash, carrying current something like I1 dash in the first, I2 dash second, I3 dash third, and we have here I4 dash. Okay, let's look back to the aim, please. Let's look back to the aim, please. What is the aim here? The aim is to find out the potential distribution across the string. Means we have to compare the voltages V1, V2, V3, V4. That's it. We have to compare the voltages V1, V2, V3, V4. For that purpose, simply I will be applying KCL at node 1 first. Okay. So KCL at node 1 means what? I2 is a current injection. Outgoing currents are I1, I1 dash. So I2 equals to I1 plus I1 dash. Okay. By using that, we will try to get the relation between the voltages. Okay. KCL at node number 1. I'll write here KCL at node number 1. KCL at node number 1 will give I2 equals to I1 plus I1 dash. I2 equals to I1 plus I1 dash. What is that current I2 we can write? What's that current I2? Simple. Look here. This is one capacitor. We are applying some voltage across the capacitor as V, let us say. We are applying some voltage across the capacitor as V. And how much is the current I, we can say? V by XC is a current drawn by that capacitor. I is equals to V by XC. Yes or no? And what you can write that V by XC? That is simply V into omega C. V into omega C. So current in a particular capacitor equals to voltage across the capacitor multiplied with omega into capacitance value. So in that way, what is the current I2 we can write? What is the current I2 we can write? V2 omega C. V2 omega C. Okay. What is that I1 we can write? V1 omega C. V1 omega C. What is I1 dash? To get that I1 dash, we should know what is the voltage across this C dash capacitor. How much voltage you can get across this? From this node to ground, na? From this node to ground. How much is that? Ground is this point only. What is that voltage you can get now? V1. That voltage will be V1 obviously. And what is the second voltage? Anybody? From this point to ground, na? This point to ground. Ground is nothing but this point. How much voltage you can get? V1 plus V2. V1 plus V2. And what is this voltage? You can say 3 to ground. Ground is this point. And how much is that voltage now? V1 plus V2 plus V3. V1 plus V2 plus V3. And last one will have V1 plus V2 plus V3 plus V4. All of you following the voltages across shunt capacitors. These are not leakage currents, please. These are not the leakage currents. These are charging currents. Yeah, let's write now. Let's write. I2 is nothing but V2 omega C. I2 is nothing but V2 omega C. What is I1? I1 is nothing but V1 omega C. V1 omega C. What is I1 dash current? This one. V1 omega C dash. V1 omega C dash. Okay. Now, you send this omega C to the other side. You send this omega C to the other side. So that V2 is equal to V1 plus V1 into C dash by C. V1 plus V1 into C dash by C. So this will be like C dash by C. You are getting it's a ratio between the shunt capacitance to self capacitance, right? Shunt capacitance to self capacitance. You are getting this ratio. That ratio we are going to call as some constant K. Let constant K equals to C dash by C. Let's take that constant K equals to C dash by C. Therefore, voltage V2, you write here. It's a ratio between shunt capacitance to self capacitance. Shunt capacitance to self capacitance. C dash by C. That's K. And what is V2 now? V1 into 1 plus C dash by C is nothing but K. So V2 equals to 1 plus K into V1. V2 equals to 1 plus K into V1. How is that K value? How is that K value you can expect? Is it greater than 1, less than 1? Positive, first of all. First of all, K value positive because it's a ratio of capacitances, right? It will be definitely positive. Positive, okay. And it may be less than 1. Practically speaking, that value may be less than 1. That comment you can make. Okay. So I'll write here always that K ratio between capacitances is positive. Always K is positive. Okay. You write here practically speaking, K will be less than 1. K will be less than 1. So whatever it is, K is positive. Na? So 1 plus some number into V1 equals to V2. 1 plus some number into V1 equals to V2. So definitely disk 2 potential is greater compared to disk 1 potential. Disk 2 potential will be greater compared to the disk 1 potential. All of you getting it? V2 greater than V1. V2 greater than V1. Okay. Now, to compare V3 with the other things, you apply KCL at node 2. What is KCL at node 2? I3 injection equal to I2 plus I2 dash. Okay. So KCL at node 2. KCL at node number 2. So you can write I3 equals to I2 plus I2 dash. I3 equals to I2 plus I2 dash. What is I3? What is I3? So it is V3 into omega C, you can say. I3 is V3 omega C, similar to the previous discussions, you can say. I2 current, V2 omega C. I2 current is V2 omega C plus I2 dash, this one. V1 plus V2 omega C dash. V1 plus V2 omega C dash. And you send omega C to the other side, So you can get V3 is equal to V2 plus V1 plus V2 into C dash by C. That C dash by C, you can call it as K. C dash by C, you can call it as K. So you can get here V3 is equal to V2 plus V1 plus V2 into K. V1 plus V2 into K. All of you understanding this? So now I'll write in the next slide. V3 is equal to V2 plus V1 into K plus V2 into K. V2 plus V1 into K plus V2 into K. So you can write now V1 into K plus you can take V2 common and you will get 1 plus K here. V2 common and you can get 1 plus K. What is that V2? V2 is V1 into 1 plus K. Na? V1 into 1 plus K already we have written. So you can get here V1 into K plus V1 into 1 plus K whole square. 1 plus K whole square. And you make this one 1 plus 3K plus K square. You will get like this. Na? So this is the disk number 3 potential. Disk number 3 potential V3 equals to 1 plus 3K plus K square into V1. 1 plus 3K plus K square into V1. Okay. So now you see here, what is V2? 1 plus K into V1. What is V3? 1 plus 3K into V1. So definitely 1 plus 3K will be greater compared to 1 plus 1 plus 3K will be greater compared to 1 plus K. So definitely V3 will be greater compared to V2 number. So I can say V3 will be definitely more compared to V2 and that is more compared to V2. V3 greater than V2 greater than V1 we can expect. Okay, next thing. Make it quick, please. Apply KCL at node number 3. That will give you relation between V4 and V3. Thereby, we will conclude KCL at node number 3. Node number 3 will give I4 is a current injection to node 3. Observe I4. Outgoing currents are I3, I3 dash. Outgoing currents are I3 and I3 dash. Okay. So what is I4? You can write V4 omega C. What is I3? V3 omega C. And what is I3 dash? You can say V1 plus V2 plus V3 into omega C dash. V1 plus V2 plus V3 into omega C dash. You send that omega C to the other side, so you can get V4 equals to V3 plus V1 plus V2 plus V3 into C dash by C is K. C dash by C is K. Now we do this one. Substitute V3 What is V3? 1 plus 3k plus k square into V1. Substitute V2, 1 plus k into V1. Substitute V3 again, 1 plus 3k plus k square into V1. Okay, so after doing that, you get some resultant equation. You get some resultant equation multiplied with V1, right? You get some resultant equation multiplied with V1. What is that resultant equation? Means it is 1 plus 6k plus 5k square plus k cube into V1. Like this, we can get it. You can get this in this. 1 plus 6k plus 5k square plus k cube into V1. This is a disk number 4 voltage. Disk number 4 voltage. Now you can observe again. This V4 is 1 plus 6k into V1. Na? V4 is 1 plus 6k into V1. That is greater compared to 1 plus 3k into V1. So finally, the conclusion what we can make is disk 4 voltage is greater compared to disk D, greater compared to disk 2, greater compared to disk number 1. This is the final conclusion what we can make. Okay? Tell me please. Tell me please. How is the potential distribution across the string you are experiencing? Is it uniform or not uniform? How is the potential distribution across the string you are experiencing? Definitely non-uniform. We have a non-uniform potential distribution across the string, right? So I can say there exists a non-uniform potential distribution or field distribution also you can say. Non-uniform field distribution sometimes you can call non-uniform potential distribution. Okay, distribution across the string. There exists a non-uniform potential distribution across the string. V4 is not conductor potential. Conductor voltage is summation of all the three, right? Conductor voltage means what? You have to measure from conductor to ground. Na? So if you are measuring the voltage from conductor to ground, what is the voltage conductor to ground? Here, if you want, you can show. Conductor to ground voltage, if you are checking, that is V1 plus V2 plus V3 plus V4. That is a conductor operating voltage. Okay, that is not the last capacitor voltage, so-called V4. That's not the last capacitor voltage, so-called V4. Okay, next, let's continue. Let's continue, please. Let's continue. So we have non-uniform potential distribution. That's okay. Now let me show that string briefly. So I'll say this is a disk number 1. We have 4 disk insulator. We are taking suspension string with the 4 units. So like this, you can say, and last one like this. Yeah, please listen. So this is a tower, transmission tower, and this is a power conductor. I can say power conductor. Please listen. These are the disk numbers 1, 2, 3, 4. We have 1, 2, 3, 4. Which disk is experiencing highest voltage? Which disk is experiencing highest voltage here? Tell me please. 4th one, right? 4th one will experience the highest voltage. So I can say the disk which is very near to power conductor. Disk which is very near to the power conductor, it will be overstressed. Right? So I can say it's a bottommost unit. Also you can say bottommost disk, or you can call this as line unit. Experiencing highest voltage compared to all. Maximum voltage also you can say highest voltage. Any name, maximum or highest voltage, comma, it is overstressed. Which disk is experiencing lowest voltage now? Which disk is experiencing lowest voltage? Topmost unit. So topmost unit, I can say here topmost disk, or you can call sometimes this as what? Tower unit. Near to tower, na? You can call it as tower unit. Tower unit. So it experiencing lowest voltage So it is under stressed. We'll say it is under stressed. It is under stressed. Okay, the disk was under stressed. See, same phenomena even you can observe in case of cable also, right? The dielectric material, what you are keeping between the conductor and sheath, the dielectric material, whatever you are keeping between conductor and sheath, the dielectric material experiencing overstress nearby the conductor, low stress nearby the sheath. Same phenomena here also. Nearby the conductor, the disk will experience overstress, and topmost disk near to the tower or near to the ground, that will be experiencing the under stress. That's it. Simple, simple. Next thing. See, for example, voltages across these units are like V1, V2, V3, V4. V1, V2, V3, V4. Please listen. Stop writing. All of you stop writing. All of you stop writing. Just listen. V1, V2, V3, V4 are the voltages. For example, I am applying a voltage 44 kV to the conductor. I am applying a voltage 44 kV to this conductor. See, listen. After applying 44 kV to this conductor, I have 4 units now. 4 units. My expectation is that each disk will experience 11 kV. Yes or no? After applying 44 kV to the conductor, my expectation is that I have 4 units. It will be equally divided so that each disk will experience a voltage of 11 kV. But unfortunately, this disk number 4 voltage V4 will come definitely more than 11 kV because of non-uniform distribution. What we are discussing, disk number 4 voltage definitely comes more than 11 kV. Then how is a disk 1 voltage? Anybody? How is a disk 1 voltage? It will be definitely less than 11 kV. Disk 1 voltage will be definitely less than 11 kV. Yes or no? I need your response. Yes or no? Yeah. Now you see. Actually, we are designing the disk with a rated voltage of 11 kV. We are taking the disk with a rated voltage of 11 kV, but the topmost units what we have, experiencing lower than 11 kV. Top units what we have experiencing lower than 11 kV means we are unable to utilize the dielectric strength of the top units. We are unable to utilize the dielectric strength of the top units. Yes or no? Yes. So how far these disks are getting utilized? How far these disks are getting utilized? So right, to tell the term, to express the term, we are introducing one point called as string efficiency. String efficiency. What it's going to tell for you? String efficiency will tell about the utilization of the disks in the string. How far you are utilizing the disks in the string, that will be given by the string efficiency. That's one thing. Other than that, we have non-uniform stress, right? Non-uniform stress or non-uniform potential distribution. The string efficiency is going to tell you how far the distribution is uniform. The voltage distribution is uniform. These two terms will be given by the string efficiency. Anyhow, I will write the things, then you will be getting some clarity about the term. Okay, so the next heading what I am going to take here is string efficiency. String efficiency. Okay, observe here. Significance of it, what it's going to tell. It gives information about uniformity in potential distribution across the string. Potential distribution across string. Uniformity in the potential distribution across the string. That's one point. Next one we are saying. It gives information about it gives information about utilization of disks in the string. Utilization of disks in the string. Okay, these two are the terms governed with the string efficiency. Now let me define it. String efficiency here. Very simple. Most of you might be knowing it already. String efficiency equal to total voltage across the string you should take in the numerator. Total voltage across the string. Across the string in the numerator by total number of units. How many? Okay. Number of disks you can say. Number of disks you can say. Multiplied with highest voltage experienced by any disk in the string. So it need not to be the bottom disk all the time. It need not to be the bottom disk all the time. So just I will say highest voltage experienced by any disk in the string. Any disk in the string. Highest voltage experienced by any disk in the string. Okay. So let's take up now, according to the 4-unit string, what we are discussing, 4-unit string. I can write string efficiency here. String efficiency. What's the total voltage across the string? Anybody please tell me. What's the total voltage across the string? V1 plus V2 plus V3 plus V4. Total voltage across the string is V1 plus V2 plus V3 plus V4. Right? How many number of units you have? 4. Which disk is experiencing highest voltage? Which disk is experiencing highest voltage? That will be 4th disk, V4. Formula I am writing. V1 plus V2 plus V3 plus V4 is the total voltage across string by 4 units multiplied with highest voltage across any disk is V4 we are showing. Okay, done. And you see, definitely this V4 is greater compared to 1, 2, 3. Na? So 4 times of V4 will come definitely greater compared to summation of these 4 voltages. 4 V4 will be definitely more compared to V1 plus V2 plus V3 plus V4. So this ratio, if you calculate, that will be definitely less than 1. So practically speaking, the string efficiency will be less than 100%. String efficiency will be definitely less than 100%. Okay. Could you please tell me what's the reason for this string efficiency becoming less than 100%? What's the reason for this? Anybody, please tell me. Simple reason I want. Why the string efficiency is becoming less than 100%? What's the reason? See, why these voltages are coming equal? V1, V2, V3, V4 are becoming unequal. The reason is I1, I2, I3, I4 currents are unequal. The reason simply here is I1, I2, I3, I4 currents are unequal. Why these currents are unequal? Because of this I1 dash, I2 dash, I3 dash, I4 dash. For example, if you don't have this I1 dash, I2 dash, I3 dash, I4 dash, if you don't have these 4 currents, then definitely 1, 2, 3, 4 currents are equal, voltages are equal, string efficiency equals to 100%. Means string efficiency is becoming less than 100% due to the charging currents drawn by shunt capacitances. Charging currents drawn by shunt capacitances. Okay. So this is due to the charging currents drawn by shunt capacitances. Okay, done. Okay, now if you compare those charging currents by these shunt capacitances, I3, I4 dash, I3 dash, I2 dash, I1 dash, here, which current is highest now? Which current is highest? Definitely I4 dash is highest now. But this I4 dash is not showing any effect actually. I4 dash is not at all showing any effect. Please listen here. Please listen here what I am saying to. Kindly observe. Why I4 and I3 are unequal? Because of I3 dash. I4, I3 are becoming unequal because of I3 dash, not because of I4 dash, right? I3, I2 are becoming unequal because of I2 dash. I2, I1 are becoming unequal because of I1 dash. So only this I1 dash, I2 dash, I3 dash will show its effect on the potential distribution across the string. I4 dash may not show any effect on the potential distribution across the string. That's why Most of the times in the textbooks are some calculations also, the bottommost capacitance what you have between conductor and tower, that shunt capacitance will be neglected in the analysis. But still it is existing. It will be there, but it won't show any effect. That's why we are not considering it in the study. All of you getting why we are not considering the last one? All of you getting this one? Why we are not considering last one? This last capacitor may not show any effect on potential distribution across the string. Yeah, so I'm explaining again. Please listen. I'm explaining again. Why voltages 1, 2, 3, 4 are becoming unequal? The reason is I1, I2, I3, I4 are becoming unequal. Okay, fine. Next, why I3, I4 are becoming unequal? Because of I3 dash current. If I3 dash is 0, I3, I4 will be equal. Na? Why I2 and I3 are becoming unequal? Because of I2 dash. Why I1, I2 are becoming unequal? Because of I1 dash. But you see, in this comparison of I1, I2, I3, I4 currents, this I4 dash is not at all coming, right? I4 dash is not at all showing that what we call its effect in the comparison between these four currents. So that these four voltages distribution is not going to be affected by the last capacitor current. Is it clear, Bhavani? Is it clear, Bhavani? Yeah, fine. Okay, so let's compare the major effective currents here, I3 dash, I2 dash, and I1 dash. The comparison will be in this way. I3 dash will be greater compared to I2 dash. That is greater compared to I1 dash generally. Okay, yeah, done. Next, let's move ahead. Now, next we'll see how is the string efficiency for the strain type string. How is a string efficiency? Look here, string efficiency for strain type string. Strain type string efficiency for strain type string. Look here, please. Look here. Strain type string means the arrangement will be in this manner. So I will show that directly in the capacitor distribution model, like this. This will be the capacitor distribution model, and you know, this is a tower. This was a tower, yeah, and it's a conductor. Next. So tower is getting grounded and operating at zero potential, of course. Each disk capacitance will be same number C. Each disk will have the same capacitance value C. Next, please listen all of you. These are the link pins formed, 1, 2, 3 link pins. 1, 2, 3 link pins formed, 1, 2, 3. Next thing. Definitely between link pin 1 and tower, there will be some shunt capacitance formation. There will be some shunt capacitance formation between link pin 1 and tower. I will call it C dash. Between link pin 2 and tower, also we get some capacitance. How is this capacitance compared to the previous number? How is the second shunt capacitance compared to the first shunt capacitance? Is it low or high? Is it low or high? Anybody, please tell me. Definitely low, because distance is more, right, Amrit? Distance is more, distance changed. So distance is more means capacitance will be less. So C double dash, I am naming it, it is less compared to C dash. We are calling that as C double dash. That number is less compared to C dash. Similarly, link pin number 3 to tower also we get a capacitance here, that is C triple dash, you can say. And the C triple dash number will be less compared to C double dash. Like this, we'll get these shunt capacitances. Now, voltages, right? Look here, voltages. First, this V1, and here it is V2, and this is V3, and this is V4. We have voltages like V1, V2, V3, V4. Voltages. Next thing, please listen, please listen. Charging currents by shunt capacitances I1 dash, I2 dash, I3 dash. Charging currents by the shunt capacitances I1 dash, I2 dash, I3 dash. Don't confuse. Same notations, whatever you have taken earlier, that I have copied here. That's it. What will be the voltage across C triple dash? Anybody? What is the voltage across C triple dash? C triple dash means between 3 to tower, right? 3 to tower means 3 to this point. 3 to this point means what? V1, V2, V3 summation. V1, V2, V3 summation. V1 plus V2 plus V3. Okay. Now, what is I3 dash current here? What is that I3 dash current? You can write I3 dash equals to V1 plus V2 plus V3 into omega C triple dash. I3 dash current will be equals to V1 plus V2 plus V3 into omega C triple dash, you can say. But you see, the C triple dash capacitance is negligibly small, right? C triple dash capacitance is negligibly small, or it is very, very low number. Very, very low number. If that's the case, how is I3 dash current? I3 dash current also expected to be very, very less. I3 dash current also expected to be very, very less. Now I'll tell you, just listen, just listen. Why you are concentrating on I3 dash? That's the question. We have many shunt capacitance currents, right? We have I1 dash, I2 dash, and I3 dash. Why you are concentrating only on I3 dash current? Why you are concentrating only on I3 dash current? Anybody? Anybody? Because that current itself is a major in the previous analysis. In the previous analysis of suspension, that current itself is a major one. So that's why I'm considering that one. So that current is coming very, very low in the sense, very, very low in the sense. Can I say a statement? Can I say a statement that overall shunt capacitance charging current is negligible? Overall shunt capacitance charging currents are negligible. Yes or no? Yes, right? So I can say that implies overall shunt capacitance charging currents are negligible. Charging currents are very low. You can write very low. So if that is the case, if that's the case, how is your string efficiency? Anybody? Anybody please tell me. How is your string efficiency of the string? How is that string efficiency? Overall shunt capacitance charging currents are very low. So string efficiency will be very high, close to 100. I will say greater than 90% all the time. Greater than 90% all the time. Particularly if you go for higher and higher levels of strings, you may touch up to 98%, 97% also practically. So I'll write here practically string efficiency. 1 minute please. I'm sorry. So practically speaking, string efficiency of the strain is more than 90% all the time. More than 90% all the time. But string efficiency of strain type string, it will be always greater compared to suspension type string with string efficiency. Strain type string efficiency will be greater compared to suspension type string efficiency. Okay, this is about strain, and I think it will be sufficient for this. Next, we'll take up the HVDC string. How will the string efficiency of HVDC string? Yeah, so I can write here string efficiency of HVDC string. HVDC string. You see, for DC operation, I already said that the disk is going to be represented as a resistor. Disk is going to be represented as a resistor. Okay, so I'll show disk 1, disk 2, disk 3, disk 4, like this. Disk 1, 2, 3, 4 we have, and there is no effect of the shunt capacitance as well as there is no effect of the self capacitance. That statement you write here first. There is no effect of shunt and self capacitances. Shunt and self capacitances. And not only that, each resistor is equal. Each resistor will be equal. So I am showing it is R simply because all the resistors are identical. No. So each resistor is capital R I am showing. Now currents, if you see, for example, if this is some current I you take, so current in each and every disk will be same, na? Current in each and every disk will be same. Now you take up the voltages here. It is V1, V2, V3, V4. These are the voltages. Voltages we have 1, 2, 3, 4. And how will be these voltages? You can say now. How will be these voltages? V1, V2, V3, V4? Definitely equal. V1, V2, V3, V4 voltages will be definitely equal. See, if these voltages are equal, how is your string efficiency? How is your string efficiency? Definitely 100%. String efficiency of the HVDC string will be equals to 100%. String efficiency of HVDC string will be equals to 100%. Yes. Following all of you? String efficiency of the HVDC string equals to 100%. Now, just look back to the 3 types what we have discussed. We discussed about HVAC suspension string. HVAC suspension string. Next, we discussed about HVAC strain type string. Now, we are discussing about HVDC string. See, I think we don't need to bother about the HVDC string. Already it is having 100%. Efficiency of it is already 100%. So I think we don't need to bother about the HVDC string at all. What about HVAC strain type? HVAC strain type, right? HVAC. HVAC strain type, good efficiency, more than 90%, close to 100 also sometimes. So I think you don't need to bother about the HVAC strain also. What about HVAC suspension? What about HVAC suspension? This is having a very low string efficiency. So we should put our concentration on the improvement of string efficiency of HVAC suspension type string only. Okay, fine. So the next heading, what we are going to take is string efficiency improvement for string efficiency improvement methods. For HVAC suspension string. Suspension type string. String efficiency improvement methods for the HVAC suspension type string. All of you getting it? A strain type is having a good efficiency, right? Strain type we have a good efficiency. Already we are touching up to 95%, 98% practically. Right. Let's think about this one. Let's think about this. See, we have voltages here V1, V2, V3, V4. Na? V1, V2, V3, V4. Just I will write it. Write these voltages first. V1, V2, V3, V4 voltages. Copying this diagram. Let's say this one. Yeah. Just look here. Just look here. V1. How is the disk 2 voltage? V2, 1 plus K into V1. Disk 2 voltage is 1 plus K into V1. Disk 3, 1 plus 3K plus K square into V1. Disk 4, 1 plus 6K plus 5K square plus K cube into V1. 1 plus 6K plus 5K square plus K cube into V1. Could you please tell me, mathematically, why these V1, V2, V3, V4 are becoming unequal? Mathematically, why these voltages V1, V2, V3, V4 are becoming unequal? Anybody? Because of K. Because of the value K. For example, if that K is 0, then obviously 1, 2, 3, 4 voltages will be equal, right? So if you maintain that K value as low as possible, then there is a chance of making these voltages a bit close, and there is a chance of getting good efficiency. Okay, so the first method to improve the string efficiency here is minimizing the value of K. Minimizing K value. Let's discuss about that here itself. Okay, what is K? C dash by C. K is nothing but C dash by C. Minimizing K. Already we discussed it, right? K. In the voltage distribution, we have said K equals to shunt capacitance to self capacitance ratio. Okay, now you see. Reducing the value of K means two options. One, increase C. Next, decrease C dash. Two options. First option, increase C. Second option, decrease C dash. Which one we suggest? See, how to increase C? C increment, how you can do it? C increment. This can be done by reducing the distance between the metal links. By decreasing the distance between the metal links, we can increase the disk capacitance value, so that K is going to be reduced. So how to decrease the distance between the metal links? That can be done by making the disk as of very thin size. If you make the disk as of very thin size, obviously capacitance C is going to be. So I can say here, C increases by reducing the size of the disk, or by reducing thickness of disk. By reducing the thickness of the disk, or you can say, use higher relative permittivity material. But this option may not be suitable for us. Why it is so means, if you are reducing thickness of the disk, voltage rating of the disk is going to be definitely reduced. That's the reason. Okay, next option is what? Decrease the value of C dash. How we can decrease the value of C dash? Anybody tell me how to decrease the value of C dash? That C dash can be reduced by increasing the distance between string and tower. Increasing the distance between string and tower is nothing but increasing the cross arm length of the tower. Okay, so this can be done by increasing cross arm length of tower. Okay, so first method, increasing the C, may not be suggested at all. Okay, and second method, we have decreasing the value of C dash. It is suggested, but up to some extent only, because cost of the tower is more, right? We are going for higher and higher lengths of cross arm, cost of the tower is going to be increased. So C dash decrement is suggested only up to some extent. In that perspective, practically speaking, in an economical way again, K value will be maintained in the range of 1 by 10 to 1 by 6. Okay, so for economical reasons, reasons, practically, K will be maintained in between 1 by 10 to 1 by 6. K less than 1 by 10 is not at all economical. That's what we are saying now. K less than 1 by 10 is not at all economical. Yeah. So I'll write here itself. K less than 1 by 10 is not at all economical. Not economical. K less than 1 by 10 is not at all economical. Okay, done. Next, we have other two methods of improving the string efficiency. Second and third methods. Let me list out here. Second method to improve the string efficiency is second method, capacitance grading technique. Capacitance grading technique is one technique we can say. Third method is providing guard wire at the conductor location. Providing guard wire at the conductor location. Providing guard wire at the conductor location. Else, you can call this method as static shielding technique. Static shielding technique. Static shielding technique. Okay, let's discuss about the second one, capacitance grading technique here. Next heading I am going to take up. The next method to improve the string efficiency. Next method to improve the string efficiency. Capacitance grading technique. Capacitance grading technique. Or you can call it as grading the insulator units. Or grading the insulator units. Grading the insulator units, you can say. Capacitance grading technique, or you can say grading the insulator units. Grading the insulator units. Yeah. Series. So we will be using unequal capacitance of the discs here. Dissimilar units are used. You can write here. Dissimilar units are used. Dissimilar units are used. So I will show those capacitances, disc capacitances here. First disc I am saying C1, second disc C2, C3, C4. Like this you can say C1, C2, C3, C4. And this was a conductor. So this is a cross arc tower connected to ground, you know. Next, shunt capacitances we have as it is. We have mentioned is a link one. Link pin 1 to tower we have C dash. This link pin 2 to tower again we have a capacitance of C dash. Link pin 3 to tower again we have a capacitance of C dash. Last capacitance we can neglect. We no need to consider it. Yeah. Next voltages you see. Voltages here V1. Disc 1. Disc 2 it is V2. Disc 3 it is V3. Disc 4 it is V4. Currents you observe quickly. Disc 1 I1, I2, and it is I3, and here you have I4. And these currents you can observe I1 dash, I2 dash, and this current is of I3 dash currents. I1 dash, I2 dash, I3 dash currents. Okay, now see, we have to find out the relationship between C1, C2, C3, C4. We have to find out the relationship between C1, C2, C3, C4, and you have to get those values. Okay. So let's say our aim is to make string efficiency 100%. See, actually, we are discussing this method to improve the string efficiency. Let us target to get 100%. Okay. So our aim is to make string efficiency equals to 100%. to get string efficiency equals to 100%. What you should do? You should make the voltages equal. V1, V2, V3, V4 voltages equal. This we should. V1, V2, V3, V4 voltage you should make equal. What is V1? V1 will be I1 into XE1. What is V2? I2 into XE2. V3, I3 into XE3. Okay. So V4 is I4 into XE4. Simple. I1 XE1, I2 XE2, I3 XE3, I4 XE2. Please listen. Please listen. How are these currents? I4, I3, I2, I1. Unequal. Currents are definitely unequal. Which current is high? I4. Because you know here, I4 is divided in two parts, I3, I3 dash. Yes or no? I3 is again divided two parts, I2, I2 dash. I2 is again divided I1, I1 dash. So definitely, I1 will be lower than I2. I2 will be lower than I3. I3 will be lower than I4. So I can say this I4 is greater compared to I3, greater compared to I2, greater compared to I2. Currents are in this order. Then how will be the reactances? Reverse order. Reactances will be in the reverse order means XE4 less than, XE3 less than, XE2 less than, XE. Reactances will be in the reverse order. Okay. So I'll show you in the next slide. XE4, XE3, XE2. So I can say here 1 by omega C4 less than 1 by omega C3, 1 by omega C2, 1 by omega C1. Omega cancelled out. Take that inverse. C4 greater than C3 greater than C2 greater than C1. These are the capacitances you can see. C4 greater than C3 greater than C2 greater than C1 you can see. Following all of you? Just maintaining this order is sufficient to get 100% efficiency. For example, I will tell you C1 value I will take 1 microfarad. C2 I will take 1.2 microfarad. C3 some 7 microfarad. C4 some 10 microfarad. Like that I have taken. Can we get efficiency 100%? No. See, just maintaining this order is not sufficient. Maintaining this order itself is not sufficient. We have to give some relationship, mathematical relation between these numbers. For that purpose, let us assume that I know the capacitance value C1 already. I know the capacitance value C1 already. So based on the C1 disk capacitance, we should find out C2, C3, C4. For that purpose, we should apply again KCLs at the node 1, node 2, node 3s. Okay, what is the node 1 KCL? I2 equals to I1 plus I1 dash. Let's write quickly. KCL at node 1. KCL at the node number 1. So you can write I2 equals to I1 plus I1 dash. Okay, what is I2 current? V2 omega C2. I2 current is V2 omega C2. What's I1 current? I1. V1 omega C1. V1 omega C1. What's I1 dash? I1 dash means you should check this voltage first, which is V1. What is this voltage? V1 plus V2. And what is this voltage? V1 plus V2 plus V3. V1 plus V2 plus V3 you can say. What's I1 dash? V1 omega C dash. This is V1 omega C dash. Like this you can. I1 dash is V1 omega C dash. And you know already V1, V2 are equal, na? V1, V2 are equal. So you can cancel. You can cancel these terms. V2 omega, V1 omega, V1 omega. Cancel. And you will get now C2 is equal to C1 plus C dash. C2 equals to C1 plus C dash. Now, let us take the constant K, what we said earlier. Let us take constant K equals to C dash by C1. Let us take that constant K equals to C dash by C1. Now we can get the C dash as K into C1. C dash we are going to get as K into C1. That you substitute here. Therefore, you can get the C2 is equal to C1 plus K into C1. C2 equals to C1 plus K into C1. And you can take that C1 common. 1 plus K into C1. This is C2. Disk 2 capacitance is equal to 1 plus K into C1. Disk 2 capacitance will be equals to 1 plus K into C1. All of you getting it? Disk 2 capacitance is 1 plus K into C1. Yeah. Next, KCL at node 2 you take. Quick. KCL at node number 2 you take. What's the node 2 KCL now? I3 equals to I2 plus I2 dash. I3 equals to I2 plus I2 dash. You can write. Take it. What is I3? V3 omega C3. V3 omega C3. What is I2? I2 is V2 omega C2. I2 dash. V1 plus V2 omega C dash. V1 plus V2 omega C dash. You said that you see that V1, V2, V3 are equal. So let's rewrite this. Let's rewrite this one. The next slide. So it is V omega C3 first term. Second term will be V omega C2. V omega C2. Next term will be 2V omega C dash. 2V omega C dash. V omega cancelled out and you will get now C3 equals to C2 plus 2C dash. C3 equals to C2 plus 2C dash. What is C2? What is C2? 1 plus K into C1. C2 is 1 plus K into C1. Okay, 2 times up. What is C dash? C dash is K into C1. So it is 2K C1. And what you will get finally? 1 plus 3K times of C1. This is the capacitance. Capacitance C3 will come to be 1 plus 3K into C1. 1 plus 3K into C1. Yeah, next. Let's take up next KCL at node 3 quickly. KCL at node 3. Make it quick, please. KCL at node number 3. What is that you write? I4 equals to I3 plus I3 dash. I4 equals to I3 plus I3 dash. What is I4? V4 omega C4. I3. V3 omega C3. What is I3 dash? V1 plus V2 plus V3 into omega C dash. Okay, now you can rewrite this one quickly. You can rewrite this. And it is V omega C4 here, V omega C3, and this is 3V omega C dash. And you will get C4 equals to C3 plus 3C dash here. C4 equals to C3 plus 3C dash. And what is C3? C3 is 1 plus 3K into C1. Plus 3C dash is 3K into C1. C dash is 3K into C1 unit. Now you can get from this 1 plus 6K times of C1. 1 plus 6K times of C1. This is a C4 capacitance. Fourth disk capacitance C. 1 plus 6K times of C1. Yeah, so all of you getting it? C1, C2, C3, C4 capacitances. Now let's take the ratio between the 4 capacitances what we have done. Or else I will tell you this one first. Look all of you. C2 equals to C1 plus C dash. Disk 2 capacitance equals to C1 plus C dash. C1 plus C dash. Okay, next thing. C3 what you have? C2 plus 2C dash. Observe here. C2 is C1 plus C dash. C3 is C2 plus 2C dash. 2C dash. What is C4? C3 plus 3C dash. C3 plus 3C dash. What is Cn? Cn minus 1 plus n minus 1 into C dash. Cn minus 1 plus n minus 1 into C dash. Okay, so I'll write nth disk capacitance. Nth disk capacitance value Cn equals to Cn minus 1 plus n minus 1 into C dash. Cn equals to Cn minus 1 plus n minus 1 into C dash, you can say. That's a nth disk capacitance. Nth disk capacitance. Getting all of you? Done? Okay, next. Let's take up that ratio, what I said now. Let's take up this ratio. C1 is to C2 is to C3 is to C4. What you can say? C2. C2 is 1 plus K into C1. C3 is 1 plus 3K into C1. C4 is 1 plus 6K into C1. That C1 will be cancelled in all. C1 will be cancelled in all. And what you will get now? 1 is to 1 plus K, 1 plus 3K, 1 plus 6K, like this you can get. 1 is to 1 plus K is to 1 plus 3K is to 1 plus 6K. What about C5, C6, C7 and so on? How will be this now? How will be this? Check this one. 1 plus 10K, 1 plus 15K, 1 plus 21K and so on. Like this. Just look here. 1 we have. K is added, 1 plus K. 2K is added, 1 plus 3K. 3K is added, 1 plus 6K. 4K is added, 1 plus 10K. 5K is added, 1 plus 15K. 6K is added, 1 plus 21K. Getting the series? Getting the series? Please tell me. I'll repeat again. 1. K is added, 1 plus K. 2K is added, 1 plus 3K. 3K is added, 1 plus 6K. 4K is added, 1 plus 10K. 5K is added, 1 plus 15K. 6K is added, 1 plus 21K. So like that, the value of capacitance should be increased starting from tower location to conductor. If you increase our capacitances in that manner, starting from tower location to conductor, definitely we get the string efficiency equals to 100%. But the main disadvantage of this method is designing of the disks of unequal sizes, right? Unequal dissimilar units, designing itself is a bit difficult. Mechanical as well as electrical design is difficult. That's why this method may not be practical to improve the string efficiency. Okay, so I'll write here electrical and mechanical design. Electrical and mechanical design of dissimilar units. Dissimilar units is difficult. So this method may not be practical to improve the string efficiency. May not be practical to improve the string efficiency. This method may not be practical to improve the string efficiency. Okay. So I think all of you getting this. So I will come back within 5 minutes and then I will start the next method. I will come back within 5 minutes. 5 minutes. Yeah, so let's start the next method. Next method of the string efficiency. That is static shielding technique. Third one, it is static shielding technique. Static shielding technique. Yeah. See, I will be going with the. Yeah. Please ask me your doubt in doubt session, Naveen Sai. Please ask me in doubt session. See, static shielding technique. See, I'm going back with the original string with similar identical units. Okay. So similar units we have to use, or identical units we have to use. Yeah. So let me show that diagram here. I'll copy from this place. 1 minute, please. So this diagram I am taking the 4 units, what we are having. 4 units. This 1, 2, 3, 4. Okay. See, this is a conductor I am showing. It's a conductor. You see, this is our cross arm. Tower connected to ground. Tower connected to ground. Listen. So each disk will have a capacitance of C, obviously. Each disk will have a capacitance of C. And there is a shunt capacitance formation here. You can call it as C dash. Shunt capacitance formation, you can call it as C dash. Like this will have C dash. Currents in the disks are I1, I2, I3, I4 currents. I1, I2, I3, I4 currents. I1, I2, I3, I4 currents. And shunt capacitances charging currents are shunt capacitance charging currents I1 dash, I2 dash, I3 dash. I1 dash, I2 dash, I3 dash are the shunt capacitances charging currents. And voltages across the disks I am showing in the blue color again. V1, V2, V3, V4. Disk voltages are V1, V2, V3, V4. Okay, let's think about this one. See, so this is the original string what we have discussed the string efficiency also, where we said this V1, V2, V3, V4 values are becoming unequal. The reason for that is this I1 dash, I2 dash, I3 dash currents. Because of these currents existence, I1, I2, I3, I4 are becoming unequal and voltage is also becoming unequal. And then we are saying string efficiency is less than 100%. For example, if you are capable to inject some current into metal link 1, if you are capable to inject some current into metal link 1 to match with I1 dash, then what will happen? Those two will be cancelled out and you can say I1, I2 will be equal. V1, V2 will also be equal. Yes or no? Now, if you are capable to inject some current into metal link 2 such that this current should match with I2 dash. This current should match with I2 dash. Then obviously I2, I3 currents are equal. V2, V3 voltage also equal. Similarly, to this, we will inject some current to match with I3 dash. Then obviously I3, I4 currents are equal. V3, V4 voltage is also equal. Following all of you. Now, the final comment what you are going to make here is, we are going to inject some currents into metal links. We are going to inject some currents into metal links 1, 2, 3, in order to cancel the shunt capacitance charging currents. Such that we will get the currents I1, I2, I3, I4 as equal and voltages V1, V2, V3, V4 also equal, and we will get the efficiency equals to 100% here. Following all of you. Right. So to inject these currents into the metal links, we will be keeping some conductor in this manner. Just we will take a piece of wire, and that wire, one end of that wire, we will connect to the conductor. We will connect to the conductor, and other end of the wire should be left free in the air. Other end of this wire should be left free in the air. And this wire we are going to name as guard wire. This wire we are naming as guard wire. All of you getting it? Guard wire. And what is the operating potential of this guard wire? It will be same as that of conductor voltage. Same as that of conductor voltage. Could you please tell me, what is conductor operating voltage? Conductor operating voltage will be summation of these voltages. So called V1 plus V2 plus V3 plus V4. V1 plus V2 plus V3 plus V4. So guard wire voltage is also the same. V1 plus V2 plus V3 plus V4. Guard wire voltage will be also the same. V1 plus V2 plus V3 plus V4. Okay. Now, please tell me. What is this node voltage? All of you following this one? Please tell me. All of you following it? Yeah. Okay. Next question I am asking you. What is this node voltage? This node means this node to ground, na? That is V1. What is this node voltage? This node to ground, na? So it will be V1 plus V2. What is this node voltage? This node to ground, na? It will be V1 plus V2 plus V3. So you observe now, there is a potential gap formation between each metal link to the guard wire. From each metal link to guard wire, there is some potential gap formation. Because of that potential gap, there will be some capacitance formation. Yes or no? That capacitance will carry the current which will be injected into the metal link, cancelling that what we call existing shunt capacitance charging current. So I will be showing capacitances formed in this manner. Capacitances got formed in this manner. And these capacitances, let me call Cx, Cy, Cz. These are going to be called as static capacitances. Static capacitances formed between the guard wire and the metal links in the string. Okay, right. So let me write the next slide. Cx. I will open the previous slide. Please kindly write this one first. These are the static capacitances formed between metal links, or you write guard wire and metal links. Guard wire and metal links. Guard wire and metal links. Static capacitances formed between guard wire and the metal links. How is the direction of current in the Cx, Cy, Cz? How will be the direction of current in the Cx, Cy, Cz? Obviously, it will be from guard wire to metal link only, because guard wire voltage is higher compared to metal link voltage. So this is the current I can say as Ix, and this is the current Iy, and this is the current I can say as Ig. Okay. So now I will write regarding the guard wire what we said. Regarding the guard wire, by providing, look here, by providing guard wire at conductor location, by providing guard wire at the conductor location. Yeah, look here. By providing guard wire at the conductor location, some charging currents are injected. Charging currents are injected. Currents are injected by static capacitances. Static capacitances to neutralize the charging currents drawn by shunt capacitances. To neutralize the charging currents drawn by shunt capacitances. And that other end we have to left free in the air. The other end of the guard wire you should left free in the air. If you connect that to any other part of your system, your conductor is connected to that. That's the problem. Your conductor will be connected to that. Okay. So by providing guard wire in the conductor location, some charging currents are injected by static capacitances to neutralize the charging currents drawn by shunt capacitances. That's it. Now, our aim, let us say 100% string efficiency now. Let's say our aim to make 100% efficiency, to make the string efficiency is equal to 100%. What you should do? You should make the voltages V1, V2, V3, V4 as equal. Should make the voltages V1, V2, V3, V4 as equal. What is V1? I1 into XE1, V2, I2 XE2. XE1, XE2, XE3 are equal, na? So I1 XE, I2 XE, I3 XE, I4 XE. Like this you can manage. I1 XE, I2 XE, I3 XE, I4 XE. I1 XE, I2 XE, I3 XE, I4 XE. And XE equal, cancel, and you'll get definitely currents as equal. I1 equal to I2 equal to I3 equals to I4. Current in each and every disk is same. Current in each and every disk is same. Yeah, practically we are using guard wire. Practically we are using guard wire. I'll tell you what is the practicality of that after a little time. Let me complete it first. Fine. So see, listen. I will ask one simple question. Very, very simple question to you. Simple question. What is the physical change? Listen my words. Listen my words. What is the physical change you are making in the method one of string efficiency? What is the physical change you are making? Cross arm length increment. That's the physical change, right? What is the physical change you are making in method 2? Method 2, what is the physical change you are making? Changing the size of the disk. Changing the size of the disk. That's the physical change you are making. What is the physical change you are making in this method? Means keeping the guard wire. Physical change means here keeping the guard wire. See, keeping the guard wire means can we keep that guard wire at any way you want. For example, I'll tell you. Just look here. This is a string I have. Let's say this is a string I have. Can we keep simply guard wire something like this? Will it improve string efficiency to 100? Or can we keep a guard wire simply like this? Will it improve to 100? Or can we keep a guard wire like this? Tell me, please. Tell me, all of you. Please tell me. Just connecting a wire is not sufficient. Huh? Just connecting a wire is not sufficient. We should keep that wire in a proper way. In the sense, we should keep that wire in a proper arrangement with respect to the string in order to cancel the shunt capacitance currents exactly. Who will decide the position of the guard wire in the string? Who will decide the position of the guard wire? That will be decided by the capacitances Cx, Cy, Cz. Okay, these three capacitances will decide the position of the guard wire. Position of guard wire in the string insulator assembly will decide the position of the guard wire. So our aim is to find out these capacitances Cx, Cy, Cz. Our aim is to find out these capacitances Cx, Cy, Cz. How? In the sense, again, by application of KCL at each and every node. Okay. So a total 3 nodes you have. Node 1 KCL you take, node 2 KCL, node 3 KCL, and we'll try to get the Cx, Cy, Cz capacitances. Based on those values, we have to decide the position of the guard wire in the string. Okay, right. What is KCL at node 1? Incoming currents 2. One is I2, next Ix. I2, Ix incoming. Outgoing I1, I1 dash. That's right. KCL at node 1. KCL at node 1. Simple, very simple now. I2 injection, Ix injection, which is equal to I1 plus I1 dash. Outgoing currents are I1, I1 dash, I1, I1 dash. I1, I2 must be equal, we said. I1, I2 must be equal, you should cancel it. Ix equals to I1 dash is a resultant. What is Ix? What is Ix here? Ix, this one. You see this side voltage, V1 plus V2 plus V3 plus V4. Other side we have V1. What is potential gap? What is the potential gap? V2 plus V3 plus V4 multiplied with omega Cx. V2 plus V3 plus V4 multiplied with omega Cx. So you can write V3 plus V4 multiplied to omega Cx. What is I1 dash? What is I1 dash? I1 dash current. V1, and this is 0, right? V1 minus 0 into omega C dash. So you can get V1 omega C dash. V1 into omega C dash. And you know already V1, V2, V3, V4 are equal. So it is 3V omega Cx equal to V omega C dash. V omega was cancelled out and Cx will come to be C dash by 3. Cx will come to be C dash by 3. C dash by 3. And let us take that K, factor K. I'll write here. Let K equals to C dash by C now. So the value of C dash will come to be K into C, right? Value of C dash will come to be K into C. Now you can keep that here. So you can write Cx equals to Kc by 3. Write that Cx as Kc by 3. Like this you can see. Cx equals to Kc by 3. This is a result from the KCL at node number 1. Okay, next. KCL at node number 2 you take. KCL at node number 2. What you can write KCL at node 2? What you can write KCL at node 2? I3, Iy, incoming. Outgoing will be I2, I3. I3 plus Iy is equal to I2 plus I2 dash. You can cancel that I2 and I3. Cancel that I2 and I3 and you will get simply Iy equals to I2 dash. Iy equals to I2 dash. What is the Iy current? Look, what is the Iy current? Iy, this current, na? So it is V1 plus V2 plus V3 plus V4 minus of V1 plus V2. So it will be V3 plus V4. V3 plus V4 into omega C1. V3 plus V4 into omega Cy. And what is I2 dash? What is I2 dash? This one. V1 plus V2 into omega C dash. V1 plus V2 into omega C dash. And it is 2V omega Cy. 2V omega Cy. And it is again 2V omega C dash. So you can get Cy equals to C dash. Cy equals to C dash. Or else you can write the Cy simply Kc. Cy you can write it as K into C. Is that okay? Class will be up to the time of finishing the syllabus. Yeah, next. Won't there be, there will be a capacitance at the fourth metal link also, but it may not show any effect. That's the thing what I am saying. May not show any effect. Okay. Next, let's continue. Cy we have done. Next, let us take KCL at this third node. I4, Iz injection. KCL at node number 3. Make it quick, please. KCL at node number 3. I4 is injection. Iz is also injection. We have I3 plus I3 dash now. I3, I4 cancel out and you will get here Iz equals to I3 dash. What is Iz? Tell me please. Iz. V1 plus V2 plus V3 plus V4 minus of V1 plus V2 plus V3 means you get V4. V4 omega Cz. V4 omega Cz. What is I3 dash? V1 plus V2 plus V3 into omega C dash. And you can get Cz equals to 3C dash. can get here Cz equals to 3C dash, or else you can write this is 3 times of Kc. Cz is equal to 3 times of Kc. All of you getting? I will explain about Salman Khan. Please ask me in doubt session. Salman Khan. Many of the people will have the same doubt. You ask me in doubt session. Yeah. Let's think back to these 3 terms here. We have Cx, Cy, Cz now. Just look here, Cx. I am rewriting the Cx. Rewriting the Cx like 1 into Kc by 4 minus 1. 1 into Kc by 4 minus 1. 4 minus 1 is 3, so it is Kc by 3. This one. 2 into Kc by 4 minus 2. Is it okay? 4 minus 2 is 2. 2 to cancel and it will be Kc. Cz. 3 into Kc by 4 minus 3. 4 minus 3 is 1. Nah? 4 minus 3 is 1. So you can get 3 into Kc by 1. It will be 3 Kc. Yeah, all of you getting it? All of you getting? Yeah. See, listen. Is there any lag? Is there any lag? Somebody is saying, Pratik, what you said regarding lag? Pratik. Yeah, somebody is saying that the screen is lagging. Screen is lagging. Pratik, kindly respond, Pratik. Screen. Okay. I don't think any network issue also here. Some delay. Okay. 1 minute. Wait, I will come back. Within 1 minute, I will come back and I will continue. 1 minute. Yeah. So let's check now. At least we queued. Seeds. See, it is 1 into Kc by 4 minus 1, 2 into Kc by 4 minus 2, 3 into Kc by 4 minus 3. What's that 4 we have here? What's that 4? What is that 4? 4. That 4 will be number of discs. 4 will be number of discs, you can see. Fine. What is the number 1, 2, 3 changing here? So you have 1 here, 1, and you have a 2 here, and you have a 3. What is it? 1, 2, 3 changing? 1, 2, 3. That will be the metal link number. Metal link number. For example, you see metal link number 1 to guard wire CX, metal link 2 to guard wire CY, metal link 3 to guard wire CJ. Okay, so I can say from first metal link to guard wire, 1 into Kc by 4 minus 2. Second metal link to guard wire, 2 into Kc by 4 minus 2. Third metal link to guard wire, 3 into Kc by 4 minus 3. Following all of you. So simply that metal link number into Kc by number of units minus metal link number. Metal link number. Like that we have to take up this. Yeah. So let me write now. Let me write. In an N-disc string insulator, N-disc string insulator, the static capacitance required from pith metal link to guard wire. Pith metal link to guard wire. Pith metal link to guard wire. So I'm calling it as CP. P is a metal link number into Kc by number of discs are N minus metal links P. So this is a way of getting that static capacitance existing from the pith metal link to guard. Yes, pith metal link to guard. Getting this? Provided that, see one thing, listen, all of you. We have to use this formula. Listen. We have to use this formula provided that you are providing the guard wire up to top metal link. Means for all metal links, if you are keeping the guard wire, this is a formula you have to provide. But sometimes in the exam, they may say that I am providing the guard wire only up to 1 metal link or 2 metal links. Like that, they will say, in that condition, you should not use this formula. Okay, to calculate the static capacitance. So this is valid only if guard wire provided up to top metal link or provided for all metal links. Provided for all metal links. For all metal links. For all the metal links. So I think all of you getting it. Next, what I'll say is, next thing. How is the position of guard wire to be kept? That's one thing I will discuss briefly. And then we'll discuss about the economy of this one little bit. Just look here. Let me copy this diagram, this one. So just listen, very simple thing. Please don't complicate. Please don't complicate. Very simple. Just observe and listen whatever I am saying. That will be sufficient to give the answers. Look, please. Look, please. I'm showing in red color. Distance between the string and tower. Distance between the string and tower. This gap, this distance. Let's say 1 meter. Let's say the distance is 1 meter. 1 or let's say 2 meters. Whatever. 2 meters. Or better not 2. You take 1 more. 1 meter gap. Distance between string and tower is 1 meter gap. 1 meter gap. What is each capacitance here? C dash. What is it? Each capacitance C dash here? Kc. Capacitance of this is Kc. This is Kc. This is also Kc. Yes or no? Response. Response please. Yes or no? Kc. Okay. Next. What is Cx value? What is Cx value got now? Cx value Kc by 3. Kc by 3. What is Cy? Kc. What is Cz? 3 Kc. Getting? Kc by 3, Kc, 3 Kc. Simple, very simple, na? Now tell me, how much distance you should keep between metal link 1 and tower? Sorry, guard wire. Metal link 1 to guard wire, how much distance you should keep? How much distance we should keep between metal link and the metal link 1 and guard wire? 3 meters. 3 meters. because capacitance is becoming by 3. Kc is a capacitance for which we have 1 meter. Now Kc by 3 you want to get means distance must be 3 times. So it will be 3 meters now. Only one person said the answer. What about remaining? Is it clear or not? This gap should be 3 meters. How much should be this gap? It will be 1 meter only because Kc capacitance, 1 meter sufficient. What is this gap? And it is Kc, so 3 Kc. So you have to keep 1 by 3 meters. 0.333 meters you should. Getting right, good. So I think all of you getting the view about the position of guard wire. Just by taking those distances, you are capable to keep the guard wire at those distances approximately. Approximately. Yes, done. This one thing. This you keep it aside completely. Next, I am saying about length of string. Length of the string length. Okay, length of string. Generally, a 20 disc insulator string, 20 disc string will be having a length of 4 meters. 20 disc string, maybe 400 kV string, 400 kV string will have a length of 4 meters. 4 meters. Okay. See, listen. See, for example, this is that 20 disc string we have. Just look, showing here. So this is a conductor. How many discs we have total? 20 discs we have. Just observe. 1, 2, 3. It is 20. It is 19. It is 18. Like that. Simple question. Length is 4 meters. Now, to improve the string efficiency of this 20 disc string, we have to provide the guard wire something like this with certain distances. We have to provide a guard wire in that manner. How much is the length of guard wire approximately? What is the length of guard wire required approximately to improve string efficiency for this one? We should not keep the guard wire close. It should be having a good distance. Tell me please, how much distance? It's not 48. No, it's not 48. 4 meters is a string length, and this length will be close to 4. Yeah, 4 meters in the sense complete string. This one, I will say this whole length is 4 meters. Okay, that's the meaning of string length. How much length? Let's say more than 4. All of you know. Let's say 5 meters. I'm saying 5 meters length of guard wire we have to use. Now listen to my question. What is the extra cost we are spending for improvement of string efficiency here? Guard wire cost. The extra cost what we are spending here is only guard wire cost. And guard wire is made by which material? Maybe guard wire. It is made by maybe steel. Sometimes maybe steel. Or maybe simply ACSR conductor also you use. ACSR conductor also. See, as you are using hundreds of kilometers length of transmission line wire, this 5 meters, 6 meters length of guard wire may not make a huge cost difference. Getting the point what I am saying? We are using hundreds of kilometers length of transmission line wire, right? Yes or no? So this at each tower 5 meters length of guard wire may not increase the cost of the system heavily. So that I can say this is a most economical method of the string efficiency improvement. It's a most economical method, as well as we can say it's a most practical method to improve the string efficiency. Okay, right. So I can say here itself at the beginning, it is a most economical and more practical method. Most economical and more practical method. More practical method to improve the string efficiency. Most economical and more practical method to improve the string efficiency, we can say. Okay, let's move back to the original slide. Now let's think about this. A 5 meters length of wire, how you can stand like that vertically? That's the question now. For example, if this is a wire here, this much length only this wire. I am standing this wire vertically like this, standing perfectly. It is observing. It's observed that it's standing perfectly. Even though there is a wind circulation, wire may not move. This wire may not move, so it is perfect. It's perfect. Same size, you take 4 meters length. Same size, you take 4 meters length. Then definitely there is a bend on the top. Definitely there will be a bend on the top. Yes or no? Not only bend. If there is a wind circulation, that wire may make some oscillation. If the wire is making some oscillation, because of those oscillations, sometimes this wire may move towards the string also. This wire may move towards the string, and that may be touching with the string. Complete flashover of the insulation is going to occur. All of you understanding? Right. So it is not possible to keep this much length of guard wire with a good mechanical strength. Yes or no? Right. So it is not possible to stand the guard wire. That's one thing what I'm saying. It's not possible to stand the guard wire of this much amount of length. But if you are using a short length of guard wire, may not be a 5 meters length. Maybe you can use only half meter or 1 meter length of guard wire, then it will stand perfect. All of you understand what I'm saying? If you are using large length of guard wire, mechanical stability is less for that. That's why it is suggested to go for short length of the guard wire. If you are going for short length of guard wire, it will stand perfect. What's your aim now? Is it to stand the guard wire or to improve efficiency? What's your aim? Is it to stand the guard wire or to improve the efficiency? Improving efficiency, right? But you are thinking how to stand the guard wire. Okay, guard wire is standing perfectly. What about our efficiency now? What about our efficiency? That should be. See, whenever you are providing the guard wire only for some bottom metal links, it is cancelling the bottom metal link shunt capacitance charging currents only. It is cancelling the bottom metal link shunt capacitance charging currents. Yes or no? Yes or no? Yes. Which are the major charging currents here? Which are the major charging currents? Bottom capacitance only, right? Bottom shunt capacitances itself are the major charging currents. Those currents are itself are getting cancelled by keeping even short length of guard wire. Then there may not be a chance of getting 100% efficiency, but definitely there is a good improvement in the string efficiency expected, even though you are providing the guard wire only for some number of bottom metal links. I think all of you understood the point what I said. So I am writing that one. Kindly listen. Practically, guard wire was kept to cover only few bottom metal links. Such that major shunt capacitance charging currents will be cancelled. Shunt capacitance charging currents will be cancelled. Major shunt capacitance charging currents will be cancelled. That implies a good improvement in string efficiency can be expected. Good improvement in the string efficiency can be expected. I think all of you getting clear? Okay, next step. See, for example, yeah, let's do some problems on this string efficiency calculations. String efficiency calculations, I will be doing some problems. Before moving to those problems, I will tell some simple concepts here. Just listen quickly. Regarding insulators, sometimes you will get this type of terminologies. What do you mean by flashover? Flashover. Flashover is nothing but electrical breakdown. Flashover is nothing but electrical breakdown. Electrical breakdown. In the sense, for example, if this is a string we have, let's say like this, the 4-disc string we have, something like this, and it's a tower, and it's a power conductor. Just listen. So because of the over voltage experienced by the power conductor, we get an arc formation from the conductor tower. From the conductor to tower, there will be an arc formation, but that arc will be forming something like this. This is called as flashover, or you can say it as electrical breakdown. Flashover, or you can say it's a electrical breakdown. Okay, and there is other term called as puncture. There is other term called as puncture. Puncture is nothing but mechanical breakdown. Mechanical breakdown means if the over voltage is very severe, then what will happen is because of the over voltage, arc will pass through the insulator, something like this. Means the insulators will be broken. And the arc will be passing through the insulator body. Okay, so this is called as puncture. Arc will pass through insulator. Arc will pass through insulator by breaking it. Okay, by breaking it. And arc will form in the air surrounding to the insulator. Arc surrounds the insulator. Arc surrounds the insulator. All of you getting it? Yeah. So there's a difference. In order to protect the insulator from flashover, sometimes to avoid this type of flashover, is to avoid the flashover surrounding that insulator, we will be keeping one element called as arcing horn. Arcing horn. It's a different element. You take this as a small heading. Just observe now. This is the insulator we have. This is the insulator. Yeah, please listen here. At the bottom end, you have guard wire, right? At the bottom end, you are keeping the guard wire, else you can call sometimes as grading ring. Guard wire, else you can say that as grading ring. Like this, we have a guard wire. This is a guard wire. And on the upper side, means at the tower location, I am keeping one more wire here. This is called as arcing horn. Just listen. I will tell in a simple way. Just listen. On the upper side, you have arcing horn, and on the bottom side, you have a guard. Listen. See this air gap here, right? Air gap. This air gap will have a strength of 30 kV by centimeters. Air gap between arcing horn and guard wire will have a strength of 30 kV by centimeter. Insulators will have high dielectric strength, maybe 60. Insulators will have high dielectric strength, maybe 60. Now you please tell me, if there is a over voltage for this conductor, which path gets breakdown first? Is it the path of insulators or air? Which path is going to be broken down first? Is it air or insulator? Air. So if there is a over voltage creation, the arc is going to be formed between these two, guard wire and the arcing horn, so that the arc will be moving away from the insulator body. Arc will be moving away from the insulator body. By that way, the life of the insulator is going to be increased. Life of the insulator is going to be increased. So the combination of arcing horn and guard wire will move the arc away from the insulator string during over voltages, so that insulator was saved from the damages. Following all of you. The combination of arcing horn and guard wire will move the arc away from insulators, away from string, such that string will be safe during over voltage. During OV over voltage, such that string will be saved from damages. String will be saved from damages. String will be saved from damages. Okay. So now let's take some problems in this insulators, particularly string efficiency calculation problems quickly. So I'm showing in the next slide. Yeah. This one. First question. Go through it, please. See, there are 20 discs in a string of insulators of a 3-phase 400 kV transmission line. String efficiency is 80%. What is the value of maximum voltage across any disc? What is the value of maximum voltage across any disc? How many discs we have here? 20. 20 discs we have. It's a 3-phase 400 kV transmission line. 400 kV means what? Line to line voltage. 400 kV is a line to line voltage. Then what is the per phase voltage of this one? Per phase voltage will be 400 by root 3. 400 by root 3 kilovolts. 400 by root 3 kilovolts. And efficiency, it is 80%. String efficiency, it is 80%. So you can write it as 0.8. Okay. And what is the value of maximum voltage across any disc? Vmax. Across any disc. And you know formula for string efficiency, right? That you use and you find it. Simple thing. What is the formula for string efficiency? String efficiency equals to total voltage across the string means V phase by number of discs N multiplied with maximum voltage across any disc. Right. So now you can write Vmax equal to phase voltage by N into string efficiency. Let's write these terms quickly. V phase 400 kV by root 3. Number of discs are 20. String efficiency is 0.8. It will be in kilovolts. 400 kV by root 3 by 20 into 0.8. How much is that? You may get 25 by root 3. You go with the options. You do that calculation according to the options given. According to the options given, we have to give in this form only. So 25 by root 3 is a correct answer to be taken. This answer is D, you can see. Correct answer is D. Maximum voltage across any disk is 25 kilovolts by root 3. 25 kV by root 3. Okay, next. Next question I am taking up. This one. Go through it. The equivalent capacitor arrangement of a two-string insulator is shown in the below figure. Okay. Maximum voltage that each unit can withstand should not exceed 17.5 kV. Means saying that maximum voltage across any unit should not be more than 17.5. The line voltage of the complete string is, this is a line. Line voltage of complete string means the string voltage you have to calculate, not line to line voltage of the system. Not the line to line voltage of the system. Okay, let's write. Let's write now. So this is a equivalent capacitor arrangement given. Equivalent capacitor arrangement given. The solution I am taking up. Solution. See this. This is the V1 value I can say, and this is a value of V2. Disk 1 and disk 2 voltages I am saying as V1 and V2. Which voltage should be 17.5 among the two? For example, you take V1 value 17.5. V1 value 17.5. V2 will come more than 17.5, which is violation of the statement. Violation of the statement. So this V2, we should take it as 17.5 kilovolts. V2, we should take it as 17.5 kilovolts. Okay. Now, what about the V1? What is the relationship between V1 and V2? V2 equals to 1 plus K into V1. So V1 equals to V2 by 1 plus K. What is capital K? C dash by C. C dash by C is what? 1 by 8. So it will be 17.5 by 1 plus 1 by 8. I think it may come like 15.55 kV. 15.55 kilovolts. Clear? 15.55. And what is the line voltage of complete string now? Line voltage of complete string, that is V1 plus V2. Line voltage of complete string, or simply you write complete string voltage. Line voltage of complete string, that value was V1 plus V2. V1 plus V2 if we take, I think it is 33.05 kilovolts. You'll get that number as 33.05 kilovolts. Complete string voltage, 33.05 kV. Done? Next thing. Let's take next problem. Next question I am taking up. Two insulator discs of identical capacitance value C. Two insulator discs of identical capacitance value C. Make up a string for 22 kV, 50 Hz. Single phase overhead line insulation system. Okay. If the pin to earth capacitance is also C, pin to earth capacitance value is also equals to C, then the string efficiency is how much? See, we have a two-disc string here. Two-disc string, something like this, you can say. Two-disc string. The pin to earth capacitance value, so-called C dash, that is also he is saying C. Pin to earth capacitance value also equals to C, what he is saying. And what is the voltage given for this conductor? 22 kV, 50 Hz frequency. Frequency is very important to take. Because if frequency is 100, efficiency will come 100%, right? frequency is 0 means efficiency will be 100%. So it is at 22 kV 50 Hz. 22 kV 50 Hz. Okay, kindly listen to me. He is asking about string efficiency calculation. That's it, string efficiency. You take this voltage V1, topmost disk, next disk is V2. Okay, and what is string efficiency formula? String efficiency formula, 2 disk string V1 plus V2 by number of disks are 2 and the highest voltage across any disk is V2. V1 plus V2 by 2 into highest voltage across any disk is V2. Okay, you please tell me what is V2 formula we have? What is that V2 formula? 1 plus K into V1. 1 plus K into V1. What is K? C dash by C. That is 1. Na? So it will come to be 2V1. V2 is equal to 2V1. Now we substitute that in this formula. So V1 plus 2V1 by 2 into V2 means it is 4V1. So it will be 3 by 4. V1 will be cancelled out and you will get that as 3 by 4. So it is 75% efficiency we can call. 75% string efficiency we can say it. 75% efficiency. So what the correct option here? B is a correct option to be chosen. Correct option is B. Okay, next. So today is the last class. Maybe after 5 minutes it will be completed and I will give some brief idea about the distribution systems. That's it. Okay. Next. Next problem. Let's say same problem, rather than 22 kV, they have given 44 kV here. Rather than 22, they have given 44. What's your answer? What's your answer? Rather than 22 kV, if they have given 44 kV, what's your answer? Remains same, right? 75% only. Remains same. It's not going to be changed. Okay, fine. Next. Let's take next problem. It's asked in GATE 2010 examination. GATE 2010 examination. This question was appeared. Yeah. Look this. Okay, that. Consider a 3-phase 50 Hz 11 kV distribution system. Each of the conductors is suspended by an insulated string having 2 identical porcelain insulators like this. Okay, so we have a 3-phase 11 kV 50 Hz system. 3-phase 11 kV 50 Hz system. Each conductor was suspended by a string like this. 2 discs we have which are identical, 5C is a capacitance. The self capacitance of the insulator is 5 times that of shunt capacitance, he said. That he has shown in the figure also. The voltages across the 2 insulators are, he has said E2 and E1. We have to find out these 2 voltages. You have to find out the values of E1 and E2. E1 and E2 voltages we have to calculate. Yeah, we'll take some separate session to complete the ESC syllabus. We'll take some separate sessions to complete the ESC extra syllabus like HVDC, PACS, smart grid, distributed generation. Okay, so let's take in the solution first. Look here. Can you please tell me what is this conductor operating voltage? Can you please tell me what is the conductor operating voltage? Anybody? 11 kV line to line voltage, na? 11 kV line to line. Then what is the conductor operating voltage? Phase voltage, right? It is 11 kV by root 3. 11 kV by root 3 means it will come to be 6.35 kilovolts. 11 kV by root 3 means it will be 6.35 kilovolts. Okay, simple. Tell me please, You can go with the formula what we have derived. You can go with the formula what we have derived to solve this problem. Else you follow the procedure what I am saying. One more. How the C and 5C are connected? How the C and 5C are connected? Parallel. C and 5C are connected in parallel. What's the equivalent now? 6C. Equivalent will be 6C. Like this you can write. 6C you can say here. Here we have 5C. 5C. And whatever the conductor to ground voltage we have, that I will show as a voltage source. Conductor to ground voltage, I will show it as voltage source. Conductor to ground voltage, I am showing as voltage source, and it's a V phase. And this voltage is E2, I can say, and this voltage is of E1. And you just apply potential division and you will get the voltages E1 and E2. Right? Apply potential division principle for this and you will get the values of E1 and E2 easy. Yes or no? Right? But capacitors voltage division. Should be very careful about it. Capacitors voltage division. So for example, if you calculate the E1 value, it is V phase into what you should say? E1. V phase into 6C by 6C plus 5C. Other capacitance should take 6C by 6C plus 5C. V phase 6.35 kV and it is 6 by 11 kilovolts. I think you may get this value 3.46 kV. 3.46 kilovolts. Getting 3.46 kilovolts. Next, E2. E2, you can write it as V phase minus E1 because sum of these two, E1 and E2 is nothing but sum of these two is nothing but V phase, right? So I can write V phase minus E1. So it is 6.35 minus 3.46. I think you may get this value 2.86 or 87 kilovolts. 2.86 kilovolts or 2.87, close number. 89, okay, sorry, 89. 89 kilovolts. So what's your answer now? E1 3.46, E2 2.89. So answer is B. Correct answer from the options given will be B. B. Okay. So this is about the overhead line insulators. Overhead line insulators. Now let's think briefly, little about the distribution system. Distribution systems. So it's chapter number 8. Okay. Distribution systems. Yeah. Distribution systems. So I'll discuss briefly about this. See, already we discussed about the definition of the distributor, feeder and all, right? Definition of the distributor, feeder and all. SAC calculations are not there for gate. SAC calculations are not there for gate. For ESC people will take some separate sessions regarding Corona, HVDC and all. Okay. This is only for the gate, what we are completing. Next. See, distributor definition, feeder definition, already we discussed in the initial stage, maybe in the introduction, we have discussed about those things. But now what we are going to discuss mainly is what will be the classification of the distribution systems in the view of connection. Okay. So classification of classification of distribution systems, with respect to connection scheme, with respect to the connection scheme, with respect to the connection scheme. Number one, radial distribution system. Radial distribution system. Second one, we will call it as ring or loop distribution system. Ring or we can say loop distribution system. Third one, we will say it is interconnected system. Interconnected system. Okay, radial system. Second one, we are saying ring or loop distribution system. And the next one, we are calling it as interconnected system. Yeah. So let's take the first one, radial system. First one, I am taking up radial distribution system. Radial distribution system. Yeah, just I will show the schematic diagram. Yeah, listen please. See, as usual, as we have this DC and AC. So we have two types of distribution systems again. DC distribution system as well as we have the AC distribution system also. So, but right now we are concentrating on the DC distribution system. Concentrating on the DC distribution system. Okay, look here. Radial, I will show one schematic diagram. Later on, we will expand it. So, it is one line simply. At various locations, we have load taps. At various locations, we will have the load tappings. And these currents are like I1, I2, I3, I4 currents. One more thing, this is one of the major assumption to be taken up in the distribution system analysis. That is, the load whatever we have is modeled as constant current at a given power factor. Load is modeled as a constant current load at a given power factor. Okay, I'll write it. Load is modeled as constant current at a given power factor. A given power factor means power factor is also constant. Does it mean? Power factor is also constant. This is one of the very, very important statement to remember in the distribution system analysis. But we are talking about DC system right now. We are talking about DC system. There is no meaning of power factor. That's why I'm showing simply currents as I1, I2, I3, I4. I1, I2, I3, I4. And this is a source location. We'll have a voltage of Vs. Let's expand this diagram to get some idea. Let us expand this diagram. See, actually, we are not having only one wire of running. Two wires will be there, forward, return. Two wires will be there. Yes or no? Right. I'll show the 2 wires. Don't write. Just listen. Just listen here. This is a forward wire, forward conductor, you can say. And this was a return conductor. I will call forward conductor and return conductor. And this side at the forward conductor, we have a DC voltage source. This side we have a DC voltage source of Vs. Now this is a point A of load tapping, point B, point C, point D. Now I'll keep the load currents. This is the load drawing a current of I1. This is a load drawing a current of I2. And this is a load drawing a current of I3. And then this is a load drawing a current of I4. Currents we have like I1, I2, I3, I4. Currents. Okay, next. Listen. See, listen. What is the current supplied by the source here? What's the current supplied by source? Summation of all the currents, right? I1 plus I2 plus I3 plus I4. Summation is nothing but the source current. Now, What is this voltage VA? Load voltage VA. Load A voltage VA. How to get it? See, if IS is a current going out from the source, definitely IS is a current coming in also. IS is a current coming in also. And you have to apply KVL for this loop, KVL for this loop. And these wires will have some resistances, definitely. Forward conductor will have some resistance. Return conductor also will have some resistance. Let me show those resistances here. Like that, we have some resistance for each and every wire, forward and return. Forward and return wires, we have some resistances. And if we apply KVL for this loop, the source voltage VS minus drop in the forward conductor minus drop in the return conductor will give the voltage VA. I'll write it. Voltage VA equals to source voltage minus IS into RF plus RR. I can write directly. I'll write it as RS plus RR. Yes or no? All of you getting it? What I've written? Tell me please. RF plus RR. See, this RF plus RR, what we have here, I will be naming it as loop resistance. Loop resistance of the section. Loop resistance of that section. Section SA. Section SA loop resistance is that RF plus RR. RF plus RR. So simply what I will try to tell here is, listen, what I will try to tell here is SA section loop resistance is R1. SA section loop resistance is R1. Then what is VA? VS minus IS into R1. R1 is a loop resistance already we have written. No? R1 is a loop resistance already we have written. Similarly, AB section loop resistance is R2, BC section R3, and this is R4. So you write R1, R2, R3, R4. These are called as loop resistances. Loop resistances of sections in distribution system. Loop resistances of the sections in the distribution system. All of you getting it? Tell me please. All of you getting this one? Okay. Yeah. See, tell me in this radial system. Okay, take 10 minutes break. Somebody is requesting me. Take 10 minutes break. 10 minutes break. After 10 minutes, we will try to finish stuff. Hardly it will take 10 minutes to complete. Why can't you wait for 10 minutes? It may take hardly 10 or 15 minutes. That's it. It's 9:35 now. And for 9:50 we'll close. 9:50 we'll close. 9:50 we'll close. Okay. Yeah, fine. See, where we are going to get the minimum voltage in the system? Where we will be getting the minimum voltage in the system? Obviously at the far end. So this is a location where we are going to get the minimum voltage. Okay, right. So you write if you want that statement also. V minimum occurs at far end. Occurs at far end of the distributor. Far end of the distributor. Next thing. What are the disadvantages of this one and what are the advantages of this particular radial system? What are the disadvantages? Disadvantage, one thing already we said, far end is experiencing low voltage. So voltage profile may not be good on the system, right? Disadvantages. Not a good voltage profile. Not a good voltage profile. Okay, this one. Next. Power loss might be a bit more. P loss may be more. Okay. Reliability of the system is less. Reliability in the sense, for example, if there is any fault on any one of the section, that section will be disconnected. Okay. After that section was disconnected, for example, this section was disconnected, you assume, then obviously I2, I3, I4 is not going to be supplied. So in that view, reliability of the system will be less, we can say. Less reliability. But advantages will be easiness in the construction as well as in operation. Easy in construction and operation. Easy in construction and operation. Easy in construction and operation. Okay. Yeah. Next. How to improve the voltage profile for this radial system? That's the question. So I'll take in the next slide a question what I said. What are the various steps we have to take to improve the voltage profile? To improve the voltage profile in radial system. In the radial system. Tell me please. To improve the voltage profile in the radial system, what we have to do? Anybody? First method, what you suggest? So simply concentrate to raise the far end voltage. What we should do? One method is keep one more source at the far end. Definitely, it will be improving the voltage profile of the system. So I'm copying the diagram. I'll keep here, and what we are suggesting now is keep one more source at far end. This is one technique. So I'll say here you'll be correcting one more source, so that definitely voltage profile is going to be. But disadvantage, again, we need two sources to supply the same system. We need two sources. That's the disadvantage. One more technique is with only single source available. So this is a system we have, a radial system here, right? So why you are keeping source at the far end? You try to keep your source maybe at the middle. So may not be exactly at midpoint. Keep at some place rather than at the end. That's it. Rather than at the end, keep at some place like this. This is a source location. And definitely both sides voltages will be improved. Okay. So keep the source at middle is the next option what we are saying. Keep the source at middle. So that will definitely improve the voltage profile. This is one thing. Yeah. So one more technique here is to improve the voltage profile. So called third one. You just join a wire from this far end D to the source. Join a wire from far end to the point S. Then definitely this D point voltage will go close to source voltage. Then obviously remaining voltage is also going to be improved, we can say. Right. So I can say here, connect a wire from far end to source. Connect a wire from far end to source. Okay. But you see here, there is a loop formation. Actually, listen. See, generally, radial system in the sense, generally the people will say there is no loop. Radial system in the sense, generally the people will say there is no loop. There is no loop means what? no loop within the forward wire, no loop within the return wire. That's meaning. But you have a loop between the forward and the return. Loop existing between forward and return, but you don't have a loop within the forward wire. That's the meaning of the radial system. But here, after connecting that wire, there's a loop formation in the forward wire, loop formation in the return wire. That system we are going to name it as loop system or ring system. So by converting radial system into ring, definitely voltage profile is going to be improved, we can say. Okay, right. So the next heading I will be taking up as ring or loop system. Ring or loop system. Okay, so for our convenience, I am showing some system like this with some currents, certain currents. So like this we'll have. So these are source location, I will say. Source location. Yes, I am calling. And these are loads A, B, C loads. A, B, C, D, E loads. Currents you can call I1, I2, I3, I4, I5 currents. Okay, loop resistances of these sections you can say like R1, R2, R3, R4, R5, R6. Loop resistances of the sections are R1, R2, R3, R4, R5, R6. Short circuit will not occur, no. Short circuit occurs if you connect the forward and return conductors directly. Yes or no? But it is a forward loop. It's a forward conductor loop only. And we have a return conductor loop also. Between those two loops, we have the loads connected. Okay, next. What are the advantages of this one? What's the advantage of this one? Good voltage profile, you can say. Good voltage profile in the system. As well as low power loss, you can call. Low power loss is one thing, right? These are the advantages, and good reliability compared to radial system. You can say it is good reliability. Good reliability. So these are the advantages you can see for this ring or loop system. Next one, it's an interconnected system now. Next one will be interconnected system. Next one, it is an interconnected system. Interconnected system. Yes, interconnected system. So here, number of sources will be interconnected together. It is one substation, I'll say substation 1. It is another substation, you will call it as substation 2. And it is another substation, you can call it as substation number 3. Substation 1, substation 2, substation 3. We have interconnections between these sources or substations, something like this. Okay. These wires you call as interconnectors. These wires you call as interconnectors. Interconnectors. Okay. From these interconnectors, we get number of distribution transformers connected. Number of distribution transformers connected like this. These are the distribution transformers. This dot what I am showing here, that's a distribution transformer. Like that, we have number of distribution transformers connected here. Like this, you can say. And here also, you can call in this manner number of substations, number of distribution transformers connected. So this is an interconnected system, and this is a system having the highest reliability compared to any other. It has a highest reliability. It has highest reliability compared to any other system. reliability compared to any other system. Any other system has the highest reliability compared to any other system. So I think all of you getting it. So how we are going to get problems in this distribution systems means two areas we can expect. One is a problem on radial distribution system fed by two sides. Radial system fed by two sides is one way of getting the problem. Other way of getting the problem is on the ring system. Okay. See, anything he is asking in the exam doesn't matter whether to calculate the resistance value of the feed distributor sections, or to calculate the currents, or to calculate the voltages or voltage drops, whatever it is, whatever way the question is asking in the exam, the first and foremost one what you have to do is find out the current distribution in each and every section. Find out the current distribution in each and every section by applying KVL. By applying KVL. So for example, if these are some current numbers I am giving you for your understanding, I am saying some numbers here. Let's say this one is drawing a current of 20, this is some 40 amperes, and this some 10, some 60, and this some 20 amperes. Like this, we have some currents done by the each and every load location. Assume that all the resistance values are given. All the resistance values are given. Please listen, please listen. We have to find out where we are getting the minimum voltage. That's the question you assume. You assume that where we are getting the minimum voltage is our question to calculate. See, for that purpose, we have to find out the current distribution in each and every section. I am saying you again and again. Any problem asked in the distribution system, first you concentrate to find out the currents in each and every section. After that, anything. Okay. So you assume some current I, which is unknown for me. I. Then what is this current? Anybody tell me, please? What is the second current? This current. I minus 20 by KCL. Yes or no? I minus 20 by using KCL. That I minus 20 is entering, 40 is drawn. Means this current will be I minus 60. So I minus 60 is entering, 10 is drawn. So this current is I minus 70. And this current will be I minus 70 minus 60. So I minus 130. And this current will be I minus 150. And simply you apply KVL for this loop, find out the current I. That's it. So apply KVL for loop. Apply KVL for loop. And find the current I. Find the current I. So after getting that current I, we came to know what is the current flow in each and every section. Current flow in each and every section. So I think all of you getting it. Tell me please. Application of KVL only. Now, for example, we have done the calculation. Let me assume. For example, we have done the calculation. And I am saying that this current I is like 80 amperes. I got the current I as 80 amperes. Tell me please. 80 amperes is entering into A, 20 drawn. Remaining current how much? 60 will flow here. 60 entering into B, 40 drawn. Remaining how much? 20 amperes will enter into this one. 20 entering into C, 10 drawn by the load. Remaining current how much? 10 amperes will come in this direction now. 10 amperes will come to the D direction. What is the load at D? 60. So 10 is injected into D, but load is 60. Then 50 amperes should come from this side. 50 amperes should come from E to D. Yes or no? And the 50 is 20, so it will be 70 here, 70 amperes. And what the resultant current supplied by the source means 80 plus 70, it will be 150 amperes supplied by the source. 150 amperes supplied by the source. All of you getting? This is a way how to calculate the currents in each and every section. Now, the next question, how you can get is, where we are going to get the minimum voltage. What is the load location at which we get the minimum voltage? Is it A, B, C, D, E? Which point? Which point? Anybody please tell me? Sir, if A, B, C, D, E is node, then directly add load will be total. Yeah, correct. What point? Yeah, listen please, listen please. See, for what load point we are getting current from both sides? For what load point we are getting current from both sides? For what load point we are getting current from both sides? D. D. For D, you are getting current from both sides. So this point will experience the lowest voltage. Okay. So V minimum occurs at load location for which there is a current supply. There is a current supply from both sides. Current supply from both sides. There is a current supply from both sides. Are we getting it? Yeah. Look here, please. Look here. See, if you are getting current to D from C you are getting to D, na? Then definitely D will be less than C, I can say. VD. Current will flow from higher voltage to lower voltage. So current is coming from C to D means C voltage is more compared to D voltage. Okay, you are getting current from B to C. B to C means B voltage is greater compared to C. And you are getting current from A to B. So A is greater compared to B. And SC is greater than E, definitely. Then you see in this way also, current you are getting from E to D means D is less compared to E voltage. And that's less compared to SC. Like that voltage. So this is the reason why you will say that the point at which we get current supply from both sides will have the minimum voltage. Okay. Same phenomena you can apply even for radial system fed by two sides also. There you have to apply KVL from one end to the other end. One end to other end you have to apply the KVL and you have to assume some current I and find out the current distribution. Check the load location where you get the current supply from both sides. That is the lowest voltage point. Okay, I will stop at this point. I will upload some problems on this one in our portal. In our student portal itself, I will be uploading some problems on this distribution system. Hardly in the complete gate history, I think 4 questions we got in distribution system. That's it. Only 4. Okay. So I'll stop at this point. If you have any doubts, you can raise your hands. So this is my mobile number 96184 61918. You can call me for any doubt. Better you call me rather than putting a message. You can put a message, that's also acceptable. I prefer to talk with you mostly to clear your doubts rather than message. Okay. So please raise your hands if anybody have a doubt. Pranjali.
Hello, sir.
Tell me, Pranjali.
Sir, in that guard wire we are using, one side is connected to the conductor and sir, the other side is free, right?
Yes.
So sir, if we connect that other side also using some insulator or something, then sir, we can keep
it's useless, right? It's useless.
Sir, okay, sir.
Again, you are connecting the insulator means that cost you have to spend, and who has to bear the weight of insulator? Tower has to bear it.
Yes, sir.
Again, that insulator will have a low efficiency again. Some issues will be there. Yes or no?
Yes, sir. Okay, sir. Thank you.
Yeah. Salman Khan.
Hello, good morning, sir.
Good morning. Tell me, Salman Khan.
That doubt about sir, how the charging current flows, sir, from conductor.
Okay. Listen. See, why you didn't get a doubt between two conductors? In the transmission lines, we said we have a charging current flow from one to the other, right?
Yes, sir.
Why we didn't get that down there?
Right, sir.
Simple, very simple. See, it is having some, sorry, it is operating at certain voltage means it is delivering some electric flux.
Yes, sir.
That electric flux is linking with the other conductor beside to that.
Right, sir.
So the second conductor is experiencing rate of change of electric flux linkage.
Right, right, sir.
What do you mean by rate of change of electric flux linkage?
EMF,
Current.
current, sir.
Rate of change of electric flux linkage is current now.
Current, current.
So there is some current induced in the second conductor due to the electric flux produced by the first conductor.
Yes, sir.
That we have to show in our circuit.
Yes, sir.
That we are saying as a charging current. That's what you can call displacement current also sometimes.
Yes, sir. Yes, sir. Understood. Sir, another doubt.
Same phenomena, wherever you see capacitor, same phenomena is going to happen. Due to the electric flux linkages, there is a current induction. That current we should show in our circuit so that we are showing the capacitor.
Okay, sir. Understood.
Okay. Yeah.
Sir, another doubt is on a 44F.
Can you please repeat what is that number?
44F, sir. 44.
44.
Yes.
Yeah. Tell me.
Sir, guard wire we only use in one side.
No. According to requirement, if it is required, you have to keep two sides also.
Two sides also.
Two sides also. For example, possible I will show the image. We have shown one image in the beginning classes, right?
Yeah.
One minute. You can see here. You can see this ring, na?
Yes, sir.
That ring itself is a grading ring or a guard wire ring.
Guard ring.
Yes, sir. It's on both sides, right?
Yes, sir. Means serve the same purpose, na, sir?
Yeah, what is it?
It serves the same purpose. Means both.
Same purpose. See, this ring what you kept here, it will act as a corona ring.
Corona ring.
This can act as a guard ring. Both. Improving string efficiency it will do, as well as protecting the system from corona also it will do.
Yes, sir. Yes, sir. Right.
Yeah.
Sir, another doubt is there. 63F.
53.
63. 63.
63. Okay.
Sir, in this we can consider it in a reverse direction also. That B has the least potential, sir.
B is having less potential.
Yeah. If we see from the another side, start from another side, circulating current.
Okay, you start from B you want.
Yeah. No.
Okay.
That's what I'm saying.
Hmm.
I'm starting from source only.
Okay, Vs
And,
is greater than Va, greater than Vb,
yes, sir.
greater than Vc, greater than Vd.
Yes, sir. Yes, sir. That's
Okay,
the point.
and it is less than E, less than yes, sir.
Yeah. That one.
So D is the lowest voltage you can see.
D is the lowest voltage, right? If I see in other way, sir, then
Tell me.
B might be coming the lowest voltage, na, sir?
B,
Yeah.
why?
If I go anti-clockwise, means from source to
From this direction you want to go?
source to E, E to D.
Okay. Vs greater than Ve,
Yes.
greater than Vd, but D is less than C, right? That is less than B, that is less than A.
Yes, sir. Understood. Yes,
Then again D is the lowest.
sir. Right.
Okay.
Okay, sir. Clear. Thank you.
Apratim Pandey.
Yes, sir.
Yeah.
Sir, I wanted to ask that there is any general equation for calculating the V voltage in the insulator?
Voltage at any disk you want.
Yes, sir.
We have one formula, but even compared to that, it is better. No, this formula. What we discussed. Okay. For example, if you want, I will tell. Listen. General formula you want. Approximate formula I will tell you. Okay. Not exact one, but I will tell you approximate. See, it's an insulator string. We have 1, 2, 3, 7, 8, 9, 10, 11, 12, like this. We have disks. Huh? First disk V1.
Yes.
Second disk 1 plus k into V1. Okay. Getting?
Yes, sir.
Third disk 1 plus 3k into V1. So 1 k is added, 1 plus k. 2k is added. 1 plus 3k. What's the next one? Next one, please tell me.
Yes, sir. 1
1
plus
plus 6k.
Yes.
What's the next one?
1 plus 9 can
10k. 10, 10. See, 1, 1, right? K is added 1 plus k. 2k is added 1 plus 3k. 3k is added 1 plus 4k. Sorry, 6k. 4k is added 1 plus 10k. Now 5k will be added. 1 plus 15k, V6. Getting?
Yes, sir.
What about V7? 1 plus 15 plus 6, 21k.
1 can.
And this will be 1 plus 28k. Like that it will be, approximately. Like this you can see. Okay.
Yes, sir.
If you want, we have some hyperbolic, what we call relations also, hyperbolic relations. For example, if you take capacitor distribution model, something like this, n units, okay, 1, 2, 3, and so on up to n. This is a shunt capacitance. You have C dash. C is a self capacitance and C dash is a shunt capacitance.
Yes.
Okay, like this you have. And this side you have a voltage source, and this side, okay, one side you have voltage source, other side you have a tower, right? 0.
Yes, sir.
Assume that on the one side you have voltage, a time loop. On the side one, else you take this is 1, 1, 2, 3, and so on up to n. N minus 1, it's n minus 2. Okay. This side you have voltage source, and this side it is shorted. Understanding?
Yes, sir.
This is a conductor portion. Huh? This is a tower. Tower is grounded, right?
Yes, sir.
So it's operating at 0 potential. Okay. Now this is x equals to 0, you assume, and this is x equals to 0 only, and this will be x equals to 1, x equals to 3, and so on up to this point is x equals to n. This point, x equal to n.
Yes, sir.
It is looking like a distributed model, na?
Yes, sir.
You have that voltage at any point x equation. Cos h gamma x into VR plus ZC sin h gamma x into IR. Have you remembered this equation in transmission lines?
Yes, sir.
X is a point where you want. VR is 0 anyhow, right? VR is 0, na? Shorted.
Yes, sir.
So this first term will be going away. It will be 0. First term will be 0. Okay.
Yeah.
Second term only
Yes.
exists. What is IR current?
Sir.
IR into ZC we should take. IR is this current. That current is nothing but this one. This current, last current, we should consider. This last capacitance may not exist. This capacitance may not exist because of short. Okay, getting?
Yes, sir.
So by using this equation, it is possible to find voltage at any point x. That's one way. That's one way of getting it. What is ZC here? Root of Z by Y. Yeah, getting.
Yes,
Are you
sir.
there? Are you there? Pandey?
My voice is not audible to you?
Yeah, it's okay now. So I have understood this technique.
Yes, sir.
So I said two techniques. One is going by this method. Second one
Okay.
is going by the equations of long transmission. Done?
Yes, sir.
Yeah. Any other doubt you have, Pandey?
No, sir. Thank you, sir.
Okay. Imtiaz,
Good morning, sir.
good morning. Tell me, Imtiaz.
Sir, I have not in that power factor correction. There is a topic, no, sir.
Okay, tell me.
Okay. Sir, we are using the shunt capacitor for the power factor correction for the increasing the voltage, irrespective of the voltage, no, sir.
Okay.
Sir, I have not means when we use that, which device will use, sir? Shunt capacitor or synchronous condenser or any other
Shunt
device?
capacitor. Practically, we are using shunt capacitors only to improve the power factor.
Sir, but if we get the over voltage, then also we
Hmm.
can increase that voltage, no, sir, in that.
No, actually, where we are going to keep the shunt capacitor bank and shunt reactor bank, that will be coming from experience. Experience in the sense, continuously we are experiencing a over voltage at certain pace from long back. Okay? Imtiaz,
Okay.
are you getting me
Yeah.
what I am saying?
No, sir, could you explain what experience
Listen,
will I
listen,
did not-
listen. For example, at some place, I am observing continuously there is an under voltage.
Okay.
Okay? So at that place, we decide to keep a capacitor bank only. Na?
Yes, sir.
So that is the way how we will decide to keep a capacitor or a reactor. For example, at
Okay, sir.
certain bus, always I am experiencing lower voltage. So let's keep a reactor there.
Okay, sir.
Okay, but as you said earlier, sir, I don't know. Sometimes there is a over voltage at that place. Sometimes there is under voltage. How to tackle both with the same device means you go with a device called as a static wire compensator, SVC.
Okay, sir.
Static wire compensator, where we will have a combination of capacitor and reactor.
Yes, sir. StatCom
Okay.
also there, no, sir.
StatCom is also an application. Yes, definitely. StatCom is also one of the applications.
Okay, sir.
Okay.
Okay, sir. Synchronous condenser, it works as a StatCom, no, sir. We're replacing the machine to the that devices.
Yes, 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 correct. Mhm.
Okay, sir. Thank you, sir.
Yeah.
That's all. Sir.
Fine. Sven,
Good morning.
good morning.
Sir, there is a problem in the bits and bytes that a VS and at an angle del and a VR at an angle 0. That is sending and receiving end voltage. And the reactance is capacitive in nature.
Oh, can you repeat again?
Sir?
Can you please repeat?
Yes, sir. The reactance is capacitive nature, means minus JXC.
Okay.
And the sending end voltage is VS at an angle del.
Okay. Tell me.
And here, then that for a stability reason.
Have you attended the stability analysis?
Yes, sir.
Already we discussed that problem, no?
That is cos of 90 plus delta, means we are getting
Whatever
sin delta
it
in
is, I
zero.
discussed that. I discussed that in analysis, right?
Yes, sir. For capacitive nature, sir, also.
No, capacitive nature load also, capacitive nature
Yes,
transfer
sir.
reactance. We discussed one problem and we have drawn the power angle curve also. In power
Yes,
system
sir.
scenario.
Actually, it is a doubt, sir. When I am solving question, it is a doubt.
Okay. Tell me what's your doubt? Yes.
Means I getting that power equation is VS into VR divided by mod X into cos
Not
of 90
modulus
plus
of X.
delta.
How you write modulus of X? You have to write X, that's it.
X.
X,
That
it's
is,
not modulus.
means
It's not modulus.
from that cos of 90 plus del also I am adding.
Then see you have transfer reactance something like this, na? Minus JX you take. And what's the parameter A? 1 at an angle 0. What's the parameter B? You write minus JX. Else you write it as X at an angle minus
X at an
90.
angle minus 90.
Listen. Then what is the power equation P? Receiving end side PR.
Yes.
mod Vs, mod Vr by mod B.
Yeah.
Mod B is
Yes.
X now. Okay.
Hmm.
Casa beta
90
minus
plus
delta.
this. Minus
Beta
90
minus
minus.
delta. And next one
This
will be
is-
0 again.
Yes.
Okay. Now we can get here mod Vs into mod Vr by X cos 90 plus delta you can write. What is cos
Yes.
90 plus delta?
That is
Minus sign
minus sign. Minus
So it
sign.
is Vs into Vr by X into sin delta with a minus sign in front of it.
Then what is the stability region? Because I'm getting that is a waveform of sine del that is passing
it
through
will be-
origin and it will be reverse.
It will be in this shape, na waveform. So if that is
Yes.
in that shape, then in which region we'll say the system is stable? Positive slope region.
Definitely for del less than 0.
Del, no. Positive slope region, the system is stable. This region we have a positive slope. This region we have a negative slope. System is unstable in this region.
But sir, when you are going to the concept that is in the class, you have said that
Okay.
to maintain the load demand, to maintain the load demand, we are dealing with dp by d
D delta.
by d del is equal to
Yeah,
1.
dp by d delta only.
Hmm.
If the dp by d delta is positive, then we will say at that point the system is stable.
But
So
here
these
in
are the
that
points
case,
at which we get the positive slope, right?
yes.
Then obviously the system is stable in that red color region, what I have shown. In this blue color region, we have
Sir,
dp by d
why
delta
not
negative.
sir, why that not in the blue region, sir?
Blue
DPR
region, if delta is
means,
increasing,
what
power
is
is
the
decreasing,
meaning
right?
of if delta is increasing, power is
Power is
decreasing.
decreasing.
Yes.
Slope, dp by d delta you calculate in this region. Slope is negative, na?
But sir, same concept means for delta increment, delta is not what is actually means delta that is in our control now. Delta is in our control.
Who said delta in our control? Delta will be controlled by load. According to load variation, delta will be commanded. Or you can say not only load, this transfer reactance is also one of the factors. Who is going to decide the delta? It's simple. You see from this equation, P is equals to P max into sine delta. Then who will decide the value of delta here? How much amount of power demand you have? What is the value of P max? These two will decide delta, right?
Load P max is constant. Okay.
P max is what? Vs into Vr by transfer reactance. Transfer reactance also decides delta.
So in the first case, P max into sine delta only, it is visible that in a delta increment, if PR is increment, then load demand will be satisfied. But
Okay.
when we go
Here
for
also
the
it will be
stability
satisfied only,
in
huh?
motor and
See, this is your initial operating point now. This is your initial operating point at which we have some angle and some power flow.
yes, sir.
Now, if delta is increasing, what will happen to power flow increasing, right? So it is meeting the power demand, system is stable.
Sir, here I am want to ask one point, sir. Let's suppose the equation in the unstable region. Let's suppose 1 point. Take 1 point.
Let's take. This is your initial point, and this amount of power. Okay.
Okay. Now I am decreasing delta. Then
decreasing
also
delta. Decreasing delta means it will come like this. But
yes.
power demand
Then,
is increasing, na?
Okay, but power demand is, but that curve also showing that the power demand it can the system can withstand that high power also means increasing
That's not the
power.
meaning here. See, whenever delta is decreasing, the meaning of that is power demand is decreasing. If power demand is decreasing, rather than decreasing the power supply, it is increasing its supply. System is increasing its supply.
Okay, means that curve is also defines the load curve.
Load curve, yes. Load variations are shown in this curve only, na?
Actually, I am drawing one line which is let's suppose this is P load. Like
okay. That load line you are saying. Okay, fine. Yes.
Like
For example,
stability.
see, this is your load line. is your load line. Okay,
Now decreasing delta in the unstable region.
decreasing the
Delta in the unstable region.
decreasing delta in the unstable region. What is happening to
Then-
power demand, power supply? This sinusoidal current
Then
is the power
supply
supply.
power is
Listen.
increasing. Then
Supply power is increasing, but your load is less. Then what will
Means
happen to
I
frequency
can
of
achieve the
operation?
demand also, no?
What is it?
Okay.
Frequency
Means
will
I
increase.
can
na?
achieve the demand also, na? If yes, power is increasing also. But
You can increase the demand. If you are increasing the demand and you are settling, that's okay. If you are increasing the demand and settling to that, that's okay. But it's not doing in that manner, right? So I'm unable to listen to you straight. Swain, can you repeat again? What's your doubt?
Means if the load is constant, then I can say that for that decreasing delta also it is stable.
Unstable only, right?
Unstable. How, sir?
No, if delta is decreasing, your supply is increasing, right? Then
Supply is increasing means this
else,
can
else you say,
achieve
else you
the.
say. Listen. Your load is decreasing. Okay, load is decreasing means what? Delta is decreasing.
Yes.
Okay, so if that load is shifting, according to that, how is your power variation? That is,
Power will be increased.
power
Okay.
will be going up, right?
Okay.
Yes or no?
Because it has a good concept on stability analysis, so I asked it.
Okay. See, you just move the load curve down. Load line, what you have done, that you make down. According to the delta will be changing. According to the delta variation, what will happen to power? Is it increasing or decreasing?
If delta is for if load is decreasing, then that delta will be shifted towards the right for unstable region.
Yeah, yes. See, for example, this is the power angle curve. Okay, see this. This is your load line. First load line, number one. This is your present delta. Okay, now you are decreasing the load, you are saying. See, whenever you are decreasing your load, something like this, you are decreasing the load, this is your new load point. But what is happening to delta? Delta is decreasing. Na? If delta is decreasing like this, then your power is increasing. Supply power is increasing.
Okay.
Then, but this is your load, right?
Okay. Now.
But you see in this one, this is your initial delta. Okay, load is decreasing and your delta is also decreasing and it may reach, right?
Okay, sir. No, okay. Means load and source must be approached to each other.
Yes. That's what we are saying, stable.
Okay.
The source should respond according to load demand positively.
Okay, sir.
Yes.
Sir, that is when we are the calculating self-inductance, LSA, LAB, LSC, that is for the line A. We are doing 0.2 ln 1 by d AB.
Okay, that's mutual. 0.2 ln 1 by DAB is mutual between AB.
Then that inside the ln term, how a unit quantity will be, means meter or kilometer quantity will be placed.
You have to keep kilometers. The distance you have to keep in meters because we are doing this one in SI units. Calculations of inductances and all we are doing in SI units, right?
ln 1 by 5 meter. It is actually, sir, right thing.
What is it?
means they are taking 0.2 ln 1 by 5 meter. DAB means let's suppose DAB is 5 meter. Then 0.2 ln 1 by 5 meter.
5 meters. Yeah, that will give you mutual inductance. Yeah. Fine, are you there? Okay, Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, that this how can it model as capacitor, sir? Because capacitor is between two conducting bodies separated by a dielectric medium with some potential gap.
Okay, yes.
Sir, that how that this can be treated as in this way, sir?
No, actually, there is some current exchange from one conductor to other conductor by means of displacement.
Yes, sir.
That current we should show in our circuit.
Yes, sir.
That we are modeling as a capacitor on the paper.
Yes, sir.
That's it. What's your doubt then?
Sir, in insulator disc, sir, means
Insulated disc is also a capacitor only, right? First metal link, second metal link. Between that, we have dielectric medium.
yes, sir. Between that leakage current will flow.
Not leakage. These are not leakage currents. These are displacement currents or charging currents.
Okay.
Leakage current we neglected. We removed the resistance from our circuit, right?
Yes, sir.
So leakage current we have neglected, which is a conduction current.
Okay, sir. Sir, means that capacitor current will flow between conductor to ground or between conductors, sir?
Conductor to ground, we have conductor to conductor, any conducting body to the other conducting body, if there's a potential gap.
Okay, sir.
Okay.
Sir, yes, sir. Sir, again that pin insulator and post insulator, that difference in post insulator means each disc have same width, sir. That one in a
Post
multi.
insulator is a different one completely.
Yes, sir. Means that images means when I saw that images, the discs are in same width, sir. Compared to pin, the disc width is decreasing from conductor to tower, sir. Means that
Okay.
you said no, sir. From rain, it will be it will like. it
Yeah.
will,
Okay. What's your doubt in
yes.
that?
Sir, what is main? That is only difference, or any difference in pin and post insulators?
That's only the difference actually between them, pin and post. Pin and
Okay.
post looking to be same, what you said,
Yes, sir.
but that post is a bit bigger one. It's larger height, you can say.
Yes, sir. Sir, means width of that will be increased. Is there any difference in voltage rating, sir?
Voltage ratings will be according to its requirement only, na?
Yes, sir.
Post insulator designed for certain voltage rating. Pin insulator might be designed for some other voltage rating. For example, if you are keeping both in the same system, will be designed for
Yes.
same voltage rating.
Yes, sir. Sir, my doubt is normally which has high voltage rating.
No, there is no meaning of saying high voltage rating. Which is having high insulation strength
Okay.
for same voltage rating will design. But which is having high strength means
Yes, sir.
post insulator will be designed with high strength compared to pin.
Okay, sir. Okay, sir. That's it, sir.
Yeah.
Thank you.
Same.
Hello, sir.
Tell me, Swain.
Sir, in case, sir.
Hello.
Swain. Are you there,
Sir.
Swain? Imtiaz.
Hello,
Tell me,
sir.
Imtiaz.
Sir, I have one doubt. I forgot that I am.
Tell me, Imtiaz.
Sir, synchronous phase modifier is there, no, sir? Sir, what is the meaning of the phase modifier in that our compensation, sir?
That's a other name they are giving phase modifier. All the shunt elements will act as a phase modifiers only. Phase modification means current phase is getting modified or not. That's the thing.
Okay, sir.
Current phase angle.
Okay, the delta.
That's now pi power factor angle. That is going to be changed or not by
Yes, sir,
adding
changing.
that phase modifier.
Yes, sir. Sir,
That is
Okay, sir. Before 2 minutes, we show about diagram of the God ring and corona ring. Is there no, sir?
Yes.
Sir, in this you have only taking only one insulator in that means one disc only in that, no, sir?
Maybe one or two it may cover.
But
This is its covering. This one is covered. This one is
yes.
covered. Maybe it will show
Only
some
two, sir.
effect on these things also, right? Some capacitance might be found, right?
Yes, sir. But
Covered
our
also.
400 kV we have more. We need the more strength, no, sir, for that. But it's using only the two discs. I thought.
Maybe that will be sufficient. Maybe up to 3 or 4 bottom metal links might be sufficient.
Okay, sir. Sir, one more, sir. In cable, but in overhead line we are using the bundle conductor as a stand.
And
stand, no, sir.
one more thing, you observe here between this power conductor and this also we have some capacitance formation.
Jumper.
Between the power conductor and the insulator.
Yes, sir.
Between these two also there is a capacitance formation, right?
Yes, sir.
That will also act as a static capacitance only.
Yes, sir. C.
Yeah. Okay, tell me what's your next term?
Sir, in overhead line for doing the symmetrical, we are using the transport, no, sir. Transporting that line. We are having the concept in the cable, sir.
Cables also it is there. That is called as bonding.
In transporting up.
Transposition only we'll do in cables also, but that name is called as bonding. Sheets bonding.
Okay.
Okay.
Sir,
Tell me.
sir, yesterday I asked that question of the discs we have in the concentric. Is there no? Sir, yesterday I saw in nearby our house we have only one disc we have in the concentric.
You show me. You send me that image once.
Okay, sir. Okay, I will send later, sir. But that insulator has only the concentric lines in that. Only one insulator. It means of the 11 kV line or the 400 kV.
Only one disc we have.
Yes, sir. Only one disc concentric,
It's
sir.
11 kV.
But the gap between that is too small, sir.
What gap?
The means the phase difference, sir.
You send me that image once. I will tell you.
Okay, sir. I will send
Me
that.
that. Okay. Swain, tell me, Swain.
Sir.
Tell me, please.
Audible, sir? Audible? Mutual inductance, that is 0.2 ln 1 by DAB, let's suppose, for LA to B. Okay. Then that DAB is a unit quantity having some meter.
Okay.
But
you may get negative.
LN
That's what your doubt is, it?
And that ln inside a quantity is a unitless. Sir, we should have unitless.
1 meter you take numerator.
Sir?
Numerator 1 meter.
Numerator 1 meter. Okay.
1 meter.
Okay. And when we calculation for power line and that okay, sir. Understand. 1 meter.
That's it. Any other doubt you have, Swain?
Thank you, sir.
Okay.
No, sir. No, sir.
Yeah. So anybody having doubt? Please raise your hands. Okay, so I think nobody's having a doubt. Thank you.
Thank you, sir.
So this is end of T&D. End of T&D. Yeah, Salman Khan, tell me.
No, I'm saying thank you, sir.
Okay. So any doubts you have, you can just yeah, who is this?
Power system 2 will continue. Power system
Okay.
2, sir.
We dealt
Means,
okay.
Okay.
Suresh.
Sir,
Do you have any doubts, Suresh? Tell me, Suresh.
sir, when will you start offline class, sir, for power system?
Offline class.
Yes, sir.
We start, I think, the day after tomorrow, 11th onwards.
11th onwards. Okay, sir. Remaining portion they till offline classes, no, sir.
Yes, yes, correct.
Okay, thank you, sir.
Okay.
Sir, I sent that picture to Telegram.
Okay, those are concentric circles only, no? What's the doubt in that? Again, 3 circles we have, that's it.
Yes, sir.
Hmm?
But
3 circles.
we are using nearby house, means we are going the 11 kV line. Sir, but the
11 kV line, one disk they are using. Okay.
Yes, sir. But the gap between the two conductor is the same as a 415, sir. That's why I'm doubt it's a 415 or the 11 kV.
You check the insulator. Other than this disk, any other insulator used on the line?
No, sir. Only this one only, sir.
With only one insulator, we run the line completely.
Not mean as that, sir. You have 3 insulators side by side, sir.
Okay, side by side. You show me that image. That image you send me, not this picture. This picture I will get in internet also, right?
Okay, sir. I will send, sir, that.
You send that image, original image.
Okay, sir.
Okay, okay.
Thank you so much.
Yeah. Okay, thank you. So I think nobody's having a doubt. So I'm closing the session. Thank you.